Hey guys, Andrew here, and welcome to my black void that I've been stuck in now for over a year. And while I was in this black void and with nothing to do, I thought to myself, I gotta pass the time somehow, so what can I do? That's when it dawned on me. Do thousands of physics problems. What better way to pass the time, right? As I'm sure you probably would agree. So that's what I've done. I've done over 1,000 physics problems, worked out step-by-step solutions just for you, just to help you through your either high school or college-based physics course. So in this video specifically, what I focus on are the pre-concepts or the prerequisites to physics. So basically we're going to focus on unit conversions, significant figures. Nobody really cares about sig figs. Uncertainty and percent uncertainty. Now, if you find these videos helpful, please give us a hand by hitting that subscribe button, the like button, and also telling your friends, all right? We appreciate it so very much. Now, without further ado, grab a pen, pencil, calculator. Come on, let's go for a ride. Number 1. The speed limit on some interstate highways is roughly 100 kilometers per hour. What is this in meters per second? Okay, so I know I have to do a basic conversion. So let's just set it up. So we have 100 kilometers per hour, and that's per 1 hour. And we're looking to convert that into meters per second. So I like to look at this basically in a 3-step process. So first we're going to take the kilometers and convert it into meters. That'll be the first part. The second part will be to take the hours and convert that into seconds. So that's part 2. And then the third part will be to divide the meters by the seconds. And we'll write the division sign there, and that's part 3. All right, so step number 1. So 100 kilometers converted into meters. So let's write down what we're given. So we're given the 100 kilometers, and I'm going to put kilometers in the bottom so that those units will cancel. And I have to see if I know a relationship between kilometers and meters. And I do, right? So I can put the meters on the top, and the relationship is 1,000 meters is equal to 1 kilometer. So now I just have to multiply across. So 100 times 1,000 will be 100,000. And that'll be in meters now. Okay, so that's the answer to part 1. Part 2 now is going to involve converting 1 hour into seconds. All right, so let's write down what we're given. We're given 1 hour. And I'm going to put hours on the bottom so the units will cancel. And I'm thinking about, could I put seconds on the top here? Well, in order for me to do so, I need to know a relationship between these two. And off the top of my head, I don't remember that. And I don't remember how many seconds there are in an hour. So that's okay. But what I do remember is how many minutes there are in an hour. And that'll be 60. Okay, great. So now the hours will cancel, leaving me with minutes. So now I'm going to write minutes on the bottom. And I'm going to see if I can now put seconds on the top. And I can, because I know a relationship between seconds and minutes. Namely that there are 60 seconds in 1 minute. So wonderful. The minutes will cancel, leaving me with seconds. And that comes out to 3,600 seconds when I do the multiplication. Step 3 now will involve doing the division, right? So the 100,000 meters that we found in part 1 will be divided now by the 3,600 seconds. So let's get out the calculator. So it's 100,000 divided by 3,600. And that works out to be approximately 27.8 meters per second. Great. So that should be the answer to part A. So now let's take a look at part B. It says now, how many miles per hour is this? Okay, so basically we have to do a very similar process, right? So we're being given the 100 kilometers per hour, per 1 hour that is. And we have to convert that into miles now per hour. So again, 3-step process. Kilometers, convert that into miles. That's the first step. Then take the hours and convert that into hours. That should be a real challenge. And then take miles and divide that by the number of hours. And that'll be step 3. Okay, so part 1. So 100 kilometers, we're going to look to convert that into miles. So let's write down what we're given. So 100 kilometers, I'm going to write the kilometers on the bottom. And I'm thinking to myself, do I know a relationship between kilometers and miles? And I do. So I can put the miles on the top. And the relationship is approximately 1.61 kilometers in every 1 mile. So take out the calculator again. It'll be 100 divided by 1.61. So that works out to be a value of 62 point around 1 miles. Okay, great. So that's the answer to part 1. Now part 2, we have to take 1 hour and convert that into hours. I guess that's just going to be 1 hour. Okay, so that should be pretty straightforward. And then part 3 is going to be to actually now do the division. So we're going to take 62.1 miles and divide that by 1 hour. And when we do that, obviously it becomes 62.1 miles per hour. Final answer. A car is traveling at a speed of 33 meters per second. What is its speed in kilometers per hour? Okay, so it looks like we have to do a conversion here. So let's write down what we're given. So we're given 33 meters per second. That's per 1 second. And we're looking to convert that into kilometers per hour. So I'd like to think about this in 3 steps. First step will be to convert meters into kilometers. Then the second step will be to convert seconds into hours. And then the third step will be to divide the kilometers by the hours. Okay, so let's take a look at step number 1. So 33 meters, convert that into kilometers. So we write down what we're given. So 33 meters. I'm going to put the meters on the bottom here and think about, do I know a relationship between meters and kilometers? And I do. So I can put the kilometer value in the numerator. And I know that for every 1 kilometer, there are 1,000 meters. Great, so when I do the math, the meters cancel out. So this should leave me with a value of 0.033 kilometers. Great, part 1 is done. Part 2. So now we're going to take 1 second and convert that into hours. So we write down what we're given, 1 second. I'm going to put the seconds in the denominator. And I'm thinking about, do I know a relationship between seconds and hours? Not directly. So maybe I do know a relationship between seconds and minutes. And I do, right? So for every 1 minute, there are 60 seconds. So the seconds will cancel. And now I'm going to put minutes in the denominator and trying to get to hours. And yes, I can put hours in the numerator because I do know a relationship between these two values. So that 1 hour is 60 minutes. Great, so the minutes cancel. So now I'm left with hours. And I have to take the value of 1 and divide it by 60 times 60. So that comes out to about 2.8 times 10 to the minus 4 hours. Great, and that's the answer to the second part. And third step now is cake. So, cake sounds good right about now. Anyway, 0.33 kilometers divided by, then our answer to step 2, which would be 2.8 times 10 to the minus 4 hours. When I do this math, I'm just going to plug it into the calculator. The answer comes out to about, I'm going to round slightly, 119 kilometers per hour. Great. That's the answer to part A. So part B now, is it exceeding the 90 kilometer per hour speed limit? Well, what did we just find? We found that the car was moving at 119 kilometers per hour, right? And the speed limit, I'll call it SL, the speed limit is 90 kilometers per hour. So yeah, right? We are definitely exceeding that speed limit. Number 3. Show that 1 meter per second is equal to 3.6 kilometers per hour. Hint. Show that the explicit steps involved in converting 1 meter per second is equal to 3.6 kilometers per hour. Okay, so basically it's just a very simple conversion. So we're looking to convert 1.0 meters per second per 1 second, and we're going to convert that into kilometers per hour. And let's see if what we convert matches up to what it should be. So I like to think about this in a 3-step process. Convert meters to kilometers. The second step will be to convert seconds into hours. And then the third step will be to divide the kilometers by the hours. Step number 3. Okay, so part number 1. 1.0 meters, convert that into kilometers. So let's write down what we're given, 1.0 meters. I'm going to write meters in the denominator and kilometers in the numerator because I do know the relationship between the two, right? There are 1,000 meters in 1 kilometer. So therefore this number should work out to be 0.001 kilometer. Great, that's the answer to part 1. Part number 2. 1 second, we're going to look to convert that into hours. So let's write down what we're given, 1 second, and we're going to write the seconds in the denominator. I don't know what the relationship is to hours, but I do know how many seconds there are in a minute. So I'm going to put that in the numerator, that every 1 minute has 60 seconds. The seconds will cancel. And then I put the minutes in the denominator next. And finally, I can put hours in the numerator because I do know the relationship. Minutes will cancel. And when I do this math, plug it into the calculator. 1 divided by 60 times 60 should be approximately 2.8 times 10 to the minus 4 hours. Great. Last but not least, step 3. Take your answer in part 1, 0.001 kilometers. Divide it by your answer from part 2, 2.8 times 10 to the minus 4 hours, and see what comes out. Plug that into the calculator, and we get, wow, 3.6 kilometers per hour. Who would have guessed? So it matches. Number 4. American football is played on a 100-yard long field, excluding the end zones. How long is this field in meters? Okay, and it also tells us to assume that 1 meter is equal to 3.281 feet. All right, so let's first start by writing down what we have, or what we know. So we know that we are starting with 100 yards, and somehow we have to convert that into meters. Now this would be a simple process if we were to know a direct conversion, but unfortunately we don't. So they do tell us, though, a conversion, right? And they give us the conversion that 1 meter is equal to 3.281 feet. So that's a way for us to convert from feet to meters, right? So the significance of that would be that I can get to meters if I were to know the feet value. But then that begs the question, can we convert from yards to feet? And if we can, then we can obviously complete this conversion circuit. And we actually can convert from yards to feet, right? Because we do know the conversion that for every, or I should say there are 3 feet in 1 yard. Okay, so knowing that conversion factor allows us to go from yards to feet, so that would be the first step. And then the second step of the problem would be to go from feet to meters. Okay, so let's start with the first step. So we want to convert 100 yards into feet. Okay, so let's write down what we're given, 100 yards. And I'm going to write yards in the denominator, feet in the numerator. And I'm going to plug in the known conversion values. 3 feet for every 1 yard. So 3 times 100 is 300. That would be feet. So that's the answer to part 1. Now basically for step 2, we're going to take that answer for part 1 of 300 feet, right, and convert that into now meters. Okay, so let's write down what we have. So 300 feet. And now I'm going to multiply by my conversion factor, put feet in the denominator, meters on the top, and plug in the conversion values. So in 1 meter, there are 3.281 feet. Great, the feet will cancel. And now, just plug it into the calculator. So 300 divided by 3.281. And I'm going to round slightly. So this works out to about 91 meters. And that would be the answer. Number 5. Soccer fields vary in size. A large soccer field is 115 meters long and 85 meters wide. What are its dimensions in feet and inches? Okay, so let's just sketch a quick picture. So here's our soccer field. So we have a 115 meter long field by 85 meters wide. Okay, great. And it sounds like what we have to do is we have to now take these meter values and convert them into feet and then into inches. So let me draw a little diagram here. So first we're going to convert it into feet, and then we're going to take that value and convert it into inches. So really this is a two-step process, the second step being feet to inches, and then the first step being meters to feet. So again, the width, we're going to take meters, turn it into feet. That's step 1. And then step 2 is going to be to convert feet into inches. Cool. So we need to know the conversion factors. So fortunately, they gave us one of them. It says that 1 meter equals 3.281 feet. So that's good. And there's one other one that we do need to know, and that the amount of inches in a foot, right? So 12 inches is equal to 1 foot. Okay, so now we should have enough information to solve the problem. So let's first work with the length of the 115 meter conversion. So let's write that down over here. So we have to, first step will be to convert 115 meters into feet. Okay, so let's write down what we're given. So 115 meters. Put meters on the bottom, feet on the top. And the numbers in the conversion factor are, there are 3.281 feet in 1 meter. So the meters cancel. Now all we have to do is multiply this across. So 115 times 3.281 feet. So this comes out to be 300, I'm going to round 77 feet. Okay, great. Now what we're going to do is we're going to take that answer from step 1 and use it in step 2, so 377 feet. And we're going to convert that into inches now. So let's write down what we're given, 377 feet, times, let's write feet in the denominator, inches in the numerator, and then the factors, right, the conversion factors. So 12 inches is 1 foot. So feet cancel, and when I do the multiplication, multiply that by 12, comes out to about, I'm going to round slightly, comes out to about 4,528 inches. Okay, wonderful. So that takes care of the length. So this is the length. Next one, let's now focus on the width. So it's basically the same process, right? So first step, we're going to take 85 meters and convert that into feet. So we're going to write down what we have, 85 meters. Put meters on the bottom, feet on the top, and then the numbers, 3.281 feet in 1 meter. Meters cancel. So now plug that into your calculator. 85 times 3.281. And again, I'm going to round. That comes out to about 279. Okay, great. That comes out to about 279 feet. Okay, now we're going to use that answer as the start of our second calculation. So 279 feet, and convert that now into inches. So let's write down our number, 279 feet multiplied by feet in the denominator, inches in the numerator, and there's 12 inches in 1 foot. So now we can cancel the feet and just take that value multiplied by 12, and we have a value of approximately 3,347 inches. That is now the width. Great. Number 6. What is the height in meters of a person who is 6 foot 1 inch tall? And it says assume that 1 meter equals 39.37 inches. Okay, so they give us a conversion value for meters to inches. Okay, so that means that if I can find out the total amount of inches, I can simply use this conversion factor to find out the meters. So let's write down what we're given. So 6 foot, 1 inch person, and somehow we have to convert this into meters. And we know that if we can find the total number of inches, we can then convert that into meters because it gave us, right, the conversion factor in the problem. Okay, so now the question is, well, how do I find the total number of inches? And that would be found simply by taking the 1 inch that was given already, and then taking the 6 foot value, right, and then adding that. So first converting the 6 feet into inches, and then adding it to the inch value already. So I'll add a little plus sign. Right, so this is essentially the first step. We'll convert it into inches. Right, then we're going to add them together. So that would be the second step. And then the third step would be simply converting the inches into meters. So let's do it. So step 1, 6 feet. Let's convert that into inches. So I'll write down what I'm given, 6 feet. Feet go on the bottom so the units cancel. Inches on the top. The relationship between the two is that there are 12 inches in 1 foot. So what we have to do here is we have to take 6 and multiply it by 12. Straightforward, 72 inches. So that's the answer to the first part. Now for the second step. I'm going to be looking to take those inches that I just found, 72 inches, and then add 1 inch to it so I can find the total height of the individual in inches. So that would just be simply 73 inches. And now the third step is to take the 73 inches, the person's total height in inches that is, and convert it into meters. So let's write down what we're given, 73 inches. Inches will go on the bottom, meters will go on the top, and now I need to know the relationship. So we look back in the problem and we know that 1 meter is equal to 39.37 inches. The inches cancel, so this basically works out to be a division. So let's plug that into the calculator. 73 divided by 39.37. And that works out to be approximately, and I'm going to round slightly, 1.85 meters. That's the final answer. Number 7. Mount Everest at 29,028 feet is the tallest mountain on Earth. What is its height in kilometers? Then it says assume that 1 kilometer equals 3,281 feet. Okay, so this seems like a fairly straightforward conversion problem. Let's write down what we need to do. So we need to convert 29,028 feet into kilometers. And they gave us the conversion factor from kilometers to feet. So this is great. It's just a simple one-step problem. So let's write down what we know. So we know we're starting with 29,028 feet. I'm going to write the feet in the denominator, kilometers on the top. Now I just have to plug in the values, right? The conversion factor, that 1 kilometer is equivalent to 3,281 feet. The feet cancel. Now all I need to simply do, take out my handy dandy calculator. So 29,028 feet, divide that by 3,281. And I'm going to round slightly, so it's going to be 8.85 kilometers. Final answer. Number 8. The speed of sound is measured to be 342 meters per second on a certain day. What is this in kilometers per hour? Okay, so it's a conversion problem. So let's write down what we need to do. So 342 meters per second, 1 second that is, right, per 1 second, must be converted into kilometers per hour. So I like to think about this in a 3-step process. First, convert the numerator value of meter into kilometer. That'll be step 1. The second step then, we're going to take the denominator value of seconds and convert that into hours separately. Last but not least, I'm going to then take the kilometers and divide it by the value of hours for my third step, and that will then give me the answer. So let's write it down. So step 1, we're going to convert 342 meters into kilometers. So let's write down what we're given. So 342 meters. Meters go on the bottom, kilometers on the top. I need to now think of a relationship between the two, right? And there are 1,000 meters in 1 kilometer. So the meters cancel. So now what I have to do is take 342 and divide it by 1,000. So that comes out to be 0.342 kilometers. Great, so that's the answer to part 1. The second part now will be to take 1 second and convert that into hours. Okay, so let's write down what we know, 1 second. Seconds on the bottom. Now, if you do know how many seconds there are in an hour, you can do this in 1 step. But I'm going to assume we don't, so I have to think of another unit to place on the top. Instead, I'm going to put meters. Not meters, minutes. That would be a weird conversion. Anyway, I'm going to put minutes. So now I'm thinking about what's the relationship between seconds and minutes? And I know that in 1 minute there are 60 seconds. So the seconds will cancel, leaving me with minutes. But now I need to get rid of the minutes, so they will go in the denominator, and the value of hour will go in the numerator. So now I need to think of the relationship between hours and minutes, and I know that in 1 hour there are 60 minutes. Great, so the minutes will cancel, leaving me now with hours. So basically, I have to take 1 and then divide it by 60 times 60. So let's plug that into the calculator. So that comes out to a value of approximately, just give myself a little space here. I'm just going to erase that. Just a little space. So 2.78 times 10 to the minus 4 hours. Okay, great. So that's the answer to the second step. And now the third step is to simply take your answer from the first step, so 0.342 kilometers, and then divide it by 2.78 times 10 to the minus 4 hours. And when we plug that into the calculator, let's do the division. I'm going to round slightly. I'm going to use a little scientific notation as well. So 1.23 times 10 to the third kilometers per hour. And that would be the final answer. Tectonic plates are large segments of the Earth's crust that move slowly. Suppose that one such plate has an average speed of 4 centimeters per year. What distance does it move in 1 second at this speed? Okay, so they're asking us to calculate a distance per time. And they don't give us the units that we need to calculate for distance, so I'm just going to assume that we can answer the distance in centimeters. All right, so let me write down what I'm given. So we have 4.0 centimeters per year, per 1 year that is. Not 1 yard, but 1 year. And this is the speed at which the tectonic plate is moving. So what we want to do is we want to try to find the distance. So I'll put a little question mark with a D there. So I want to find the distance that this tectonic plate travels in 1 second, or AKA per 1 second. So basically what I can do here is I can convert, if we're looking at how this is set up, I can take the year value and convert that into seconds. Okay, what that then would allow me to do is that would then allow me to calculate the centimeters that this tectonic plate would be moving per second. All right, so let's give that a shot. So step 1 here, let's take 1 year and convert that into seconds. So let's write down what we're given, 1 year. And we're going to write year on the bottom. I have no idea how many seconds there are in a year, but I do know, let's say how many days there are. So 365 days. So I can put that conversion in the numerator. I notice I did the yard thing again. I don't know. I'm not really sure why I'm confusing years with yards. I think that's because I just did a problem with yards. Anyway, So there, in 1 year, there are 365 days. So the years would cancel. That would tell me how many days there are. I know some of you might be saying, well, there's really 365 and a quarter days. That's true. Just going to simplify it here. So then what I'm going to do is I'm going to put days in the denominator here because I need to get rid of it. And I know the relationship between days and, let's say, hours, right? I know how many hours there are in a day. There's 24 hours in one day. So I'm getting closer to seconds. I'm getting smaller, right? Now I'm going to put hours on the bottom. And I don't quite know the relationship to seconds yet, but I do know the relationship between minutes and hours. There's 60 minutes in an hour. So I got rid of hours. And now I can put the minutes on the bottom, seconds on the top. And there's 60 seconds in a minute. Minutes cancel. And finally, I can find the value. So 365 times 24 times 60 times 60 gives us a total of a whopping 3.15 times 10 raised to the, I gotta count this one out actually, 7 it looks like, to the 7 seconds. Okay. So that's how many seconds there are in a year. Okay, great. Now remember, this tectonic plate is going to move 4 centimeters, right, per year. So if I want to find out how far this tectonic plate will travel per second, what I can do now in step 2 is I can take my 4 centimeter value and then divide it by the seconds that I found. So 3.15 times 10 to the 7 seconds. Okay. I don't know if you hear my little guy crying in the background, but it must be bedtime. So let's take the 4 centimeters and divide it by 3.15 raised to the 7. Okay, so that gives me a value of 1.3 approximately times 10 to the negative 7 centimeters per second. And that should make sense, right? I mean, if this tectonic plate is going to travel 4 centimeters in a whole year, then it should be traveling a very small fraction of centimeters in 1 second. So this would be the answer to part A. And now it asks us, okay, so that's A, and then it asks us now to find its speed in kilometers per million years. Okay, so basically what I want to do is I want to now, let me write down over here, I'll write part 2, or this is really step B. Right, so now what I'm going to be thinking about is I'm given the value again of 4 centimeters per 1 year. Right, and now what I need to do is I need to find the speed in kilometers. So kilometers per million years. Okay, so 3-step process. It's going to be slightly different than the processes we usually do. First, let's take the centimeters and convert it into kilometers. Okay, let's do that first here. So part 1. So 4.0 centimeters, convert that into kilometers. So I'm going to write that down here, 4.0 centimeters. Times I'm going to write centimeters in the denominator, meters on the top. I know there's 100 centimeters in a meter, so that's great. And then the next relationship would be meters on the bottom, kilometers on the top, because I know that relationship. So it's 1 kilometer for every 1,000 meters. So that cancels, right? So now I'm going to take 4, divide it by 100, and then divide it again by 1,000. So this comes out to be 4 times 10 to the minus 5 kilometers. So now let's think. So this is basically how far it travels, right? 4 times 10 to the minus 5 kilometers in 1 year. Okay, so this value is really still per year because I didn't convert the year value. But I don't want to know the kilometers per year. I want to know the kilometers per million years. So again, if it travels 4 times 10 to the minus 5 kilometers in a single year, then what I can do is I can simply take this kilometer value and multiply it by 1 million, and that will now give me the total distance traveled, right, per million years. Okay, so now let's take the 4.5, not the 4, the 4 times 10 to the minus 5, and multiply that by 1 million. Okay, and it comes out to be a value of 40. So it travels 40 kilometers per million years. And that would be the final answer for letter B. And this should make intuitive sense, right? Going back, just double checking. If it travels 4 centimeters in a single year, right, then over 1,000,000 years, which is a long time, it should travel about 40 kilometers. It does make intuitive sense. So we're on the right track. Number 10. A. Refer to Table 1.3 to determine the average distance between the Earth and the Sun. Then calculate the average speed of the Earth in its orbit in kilometers per second. Okay, so if you were to go to the book and you look up Table 1.3, you'll find that the distance between the Earth and the Sun is going to be the value of 10 raised to the 11 meters. So let me draw a simple picture. So let's say here's the Earth as a dot, and then let's call this object the Sun. So here's the Sun and here's the Earth, right? And the distance between the two, as it says in the book, is 10 raised to the 11 meters. Okay, so now it wants to calculate the average speed of the Earth in its orbit in kilometers per second. All right, so what we need to do first is we need to conceptualize, well, how does the Earth travel around the Sun? Well, it travels in an orbit, right? And it travels in a circular orbit. Well, it's not totally circular, but let's just assume it's a perfect circle for this problem. So I'm going to draw now its orbit. And what a beautiful circle. Okay, so here's the circle, if you can call it that. And if I had to calculate now the distance of this circle, right, or not the distance of the circle, but the distance of the circumference, right, that's what this represents, this particular distance, we could do that by using the circumference formula. Okay, so let me write that down over here. So the circumference formula is circumference of a circle is equal to 2 pi times the radius. Okay, so remember, the circumference of the circle I drew is really the distance the Earth will travel. Okay, so let's calculate that first. So circumference will equal 2 times pi times the radius, which was 10 raised to the 11. Okay, and by the way, that's in meters, right? So the circumference of the orbit is going to be 2 times pi times 10 raised to the 11. Oop. Hold on, just plugged it in improperly. 2 times pi times 10 raised to the 11. Okay, here we go. So works out to be approximately 6.3 times 10 to the 11 meters. Okay, that is going to be the distance that the Earth travels. So this equals the distance. Okay, great. Now, if I were to ask you, how long does it take the Earth to travel around the Sun? You say, oh, it takes a year. Okay, and that would be correct. So now what I can do is basically I can reformat this distance to really be a speed, right? By doing the following. So what I'm going to do is I'm going to take the distance, 6.23 times 10 raised to the 11 meters, and I'm going to divide it by 1 year. Okay, what does that do for me? Well, now it gives me a speed. It gives me a rate, right? It tells me the distance that the Earth is traveling per year. Okay, so the math works out simply here. 6.23 times 10 raised to the 11 meters per year. Okay, now what this problem turns out to be is now it is a simple conversion problem. Okay, so I did all that work prior so I can make it or turn it into a conversion problem. So basically now the problem will be this. 6.23 times 10 raised to the 11 meters per year. And what I need to do is I need to convert that now into kilometers per second. So remember, 3-step process. And remember, this is always per 1 year. So first convert the meters to kilometers. That's step 1. Step 2 will be to convert the years into seconds. And then step 3 is going to be to divide the kilometers by the seconds. Okay, so step 1. 6.23 times 10 raised to the 11 meters, convert that into kilometers. So 6.23 times 10 raised to the 11 meters, meters on the bottom, kilometers on the top, and the relationship is 1 kilometer for every 1,000 meters. Great, so the meters will cancel. So now I can simply take this and divide by the 1,000. So this works out to be 6.23 times 10 times 10 raised to the 8 kilometers. Okay, so we're good there. Now step number 2 was now to convert the 1 year into seconds. Okay, so let's write down what we have. We have 1 year. Years on the bottom. Well, if I know how many seconds there are in a year, I can put seconds on the top, but I don't. So let me do days first. So there's 365 days in 1 year. Great, so that gets rid of the years. Then I'm going to write days on the bottom. And now I know how many hours there are in a day. Right, 24 hours in a day. So now the days cancel. Then I know how many minutes there are in an hour. 60 minutes in an hour, so the hours cancel. And then minutes on the bottom. And now finally seconds on the top. 60 seconds in a minute. Oh, all right. So now we can calculate this all out. So 365 times 24 times 60 times 60. And I'm going to round. So 3.15 times 10 raised to the, just count, looks like 7. So 10 raised to the 7 seconds. Okay, great. Now all we have to do is simply take the answer to part A, or not part A, but part 1. Right, so 6.23 times 10 raised to the 8 kilometers, and then divide that by 3.15 times 10 raised to the 7 seconds. And when I do this, I will now find kilometers per second. So let me plug that into the calculator. To the 8 divided by that answer. So this comes out to about 19.8 or so. 19.8 kilometers per second. Okay. That would now be the answer to part A. So that's the rate in kilometers per second. Now what we need to know is we need to find, it asks us for part B, but it says find the rate, the speed that is, in meters per second. All right, so let's use our answer we found right here, the 19.8 kilometers per second, and let's do a very simple conversion. So I'm going to do that here. I'll actually do it on the top line. All right, so I'm going to write letter B here. Okay, letter B. So it looks like we're going to take the 19.8 kilometers per second. Let me just rewrite that so to make it a little neater, per 1 second. And we're going to convert that into meters per second. All right, so the only unit that changes here is the numerator value. It goes from kilometer to meter. And if you notice, the denominator stays the same. So I don't have to do anything with that denominator. So I just got to convert the numerator value. And that will be the answer. So let's take the 19.8 kilometers. I'm going to put kilometers on the bottom, meters on the top, so that the kilometers cancel. Now I think about my relationship. There's 1,000 meters in a kilometer. Great. So now I just have to multiply it out, right? So you can plug that into the calculator. So 19.8 times 1,000. This is easy enough. You probably don't even need the calculator. Right, so this comes out to 1.98 times 10, converted into scientific notation here, raised to the 4 meters. And then, that's the answer, right? And now all I have to do is place this value over 1 second, and that's the rate. So, it just becomes 1.98 times 10 to the 4 meters per second. Final answer. Number 11. Suppose that your bathroom scale reads your mass as 65 kilograms with a 3% uncertainty. What is the uncertainty in your mass in kilograms? Okay, so first, what does this term uncertainty mean? Well, I think we can kind of all agree that it means that we're unsure, right? So, okay, we're unsure. So the scale reads out. So when you step on this thing, right, you step on the scale. I don't know what this is, but pretend it's a scale. And you step on it, and the scale will read 65 kilograms. But there's a 3% uncertainty associated with this measurement. So what that means is we're really unsure, and we're unsure by the value of 3%. Okay, so 3% of what? Well, 3% of the mass that was detected, right, of the 65 kilograms. So when we're unsure, right, maybe the true mass is 65 kilograms, right? Or maybe it's not. Maybe it's 64 kilograms, or maybe it's 66 kilograms, right? It could be a little lower, or it could be a little higher. So this term uncertainty, I always want you to remember it as a plus or minus value. Okay? So how to solve this particular problem is we take the mass, so we have 65 kilograms, that's what it measures, and then there's a 3% uncertainty associated with that. So let's take that value and multiply it by 3%. But remember, whenever you multiply percents, you really have to convert them into their decimal forms. Okay, so 65 times 0.03. So this comes out to be 1.95 kilograms. Okay, so this is the uncertainty. This value right here, uncertainty. Okay. Now, remember, uncertainty implies a plus or minus. So the only thing that I need to add into this value of the uncertainty is the plus or minus sign, because maybe it's plus 1.9 kilograms, or maybe it's minus 1.9 kilograms. So let me add that in now. So kilograms. So this is now the uncertainty. Okay. And now what we can do is now we can find the bounds of the uncertainty, right? So meaning I can take the original mass, 65 kilograms, add to that the 1.95 value of the uncertainty, and find the upper limit of the uncertainty. So just take out your calculator, plug that on in, and it comes out to 66.95 kilograms. That's the upper limit of the uncertainty. And then to find the lower limit of the uncertainty, just subtract the 1.95 kilogram value. So the lower bounds will be 65 minus 1.95. So it comes out to 63.05 kilograms. So this would be the range that I just drew right in here. Okay. And again, you can write it that way. Another way to write it in a condensed fashion would be to write something in this fashion. 65 kilograms plus or minus 1.95 kilograms. That would be a condensed way to write it instead of writing the upper and lower bounds. But all these should be acceptable. Number 12. A good quality measuring tape can be off by 0.5 centimeters over a distance of 20 meters. What is its percent uncertainty? Okay, so probably an easy way to think about percent uncertainty is to think about this particular formula. So let's write it down. So percent uncertainty, I'm just going to call it UNC for uncertainty. Percent uncertainty is equal to the value that it's off by, value I'll just write off by, divided by the distance of the measurement multiplied by 100. Okay? So that's a fairly, you're not going to see this, by the way, this formula written in this way in the textbooks. This is a commonsensical formula. Okay? So think about percent uncertainty as the value that the measurement is off by divided by the total distance of the measurement that was taken, and then multiply that by 100. So if we use this simple model, the uncertainty or the percent uncertainty should be 0.50 centimeters divided by 20 meters times 100. Okay. Oh boy. Sorry. That's my son in the background. If you hear him, I do apologize. He sounds very happy, though, which is good. Anyway, so now when I take a look at this, I notice one thing. So don't rush to plug it into the calculator, because there's one thing that you have to make certain of before you do this. Okay? Take a look at the units, okay, of your calculation. These units better be consistent with one another. What do I mean? They better be the same. If they're not the same, the calculation will not come out correctly, because the percent value, the percent is essentially unitless. So what does that mean? That means the units have to cancel. And if I have centimeters in the numerator and meters in the denominator, they don't cancel. So therefore, I can't really calculate it at the moment. So I just have to make sure that both of them are the same. Now, it doesn't matter if you take the 0.5 centimeters and convert that into meters, or you took the 20 meters and converted that into centimeters. You would still get the same percent uncertainty. So let me do this. Let me take, on the right-hand side, I'm going to start writing. So let me take the 0.50 centimeters and just convert that into meters. So write down what we're given. Centimeters will go on the bottom, meters on the top, and we have, for every 1 meter, there's 100 centimeters, right? So now converting this into meters, we would just have to move, essentially, you can plug it into the calculator, but you can just move the decimal 2 places to the left, right? So it should be 0050. So 1, 2, and that's in meters now. Okay, now this is the number we can use in our calculations. So I'll write it here, 0.0050 meters. And let me set up the rest of the uncertainty calculation, right? This was over the 20 meters multiplied by 100, percent uncertainty. And now just plug that into the calculator, 0.005 divided by 20 times 100. And the value comes out to be, percent uncertainty, comes out to be 0.025%. And that would be the final answer. Number 13. A car speedometer has a 5% uncertainty. What is the range of possible speeds when it reads 90 kilometers per hour? All right. So basically, uncertainty means, right, that we're unsure of our measurement, right? And we're unsure either plus 5% or minus 5%. So remember, uncertainty always comes along with this plus or minus value. So if I were to write out, let's just say a simple equation that represented the measured speed and the uncertainty, it would look something like this. So we would write down 90 kilometers per hour plus or minus 5.0%. Okay, this would be the measured value, including the uncertainty. So here is the measured, S-U-R-E-D, measured value, and here is the uncertainty. Okay, so first question is, well, 5%, that's great, that's the uncertainty, but 5% of what? Right? Percents are always of something. So 5% of the measurement, that's what they're talking about. All right, so now when it says, back to the question, what is the range of possible speeds? Well, it looks like now we actually have to calculate 5% of 90 because we need to give the range. So let's write that down. So I'm going to write it right beneath. So there's going to be 90 kilometers per hour, right? Plus or minus 5%, 5.0% of 90. Okay, great. Now I can simply calculate this on out, right? Just take that. I'm going to rewrite it. Just take it, though, and plug it into your calculator. So plus or minus. So we have 0.05. Remember, when you multiply by percent, you have to convert it to the decimal. Just move the decimal point 2 places to the left. And then take that percent and the decimal form, that is 0.05, multiplied by 90. And that should come out to a value of 4.5. So here's now the new uncertainty with units of kilometers per hour. Right before, it was just a percent value. Right? So even being a little, let's say, more clear here, what I'll do is let me just erase this parenthesis there. And let me actually plug in the units, right? Because it's really 90 kilometers per hour. So that's how you can clearly see now how we got to the units here. Okay, then it says just give the range. Now this could be an acceptable answer that I boxed in, but if they actually wanted the upper limit and the lower limit, all we would have to do is break this equation up into two parts. Okay, both the plus and the minus. So now what I'm going to do is I'm going to write 90 kilometers per hour plus 4.5 kilometers per hour. And since the units are the same, I can simply add it. Right, so the upper limit of the uncertainty will be 94.5 kilometers per hour. Okay, wonderful. And then the lower limit would be 90 kilometers per hour minus 4.5 kilometers per hour. Right, and that should now work out to be 85.5 kilometers per hour. Okay, so here's the upper limit, and here is the lower limit. Okay, so that's great. That should be a complete answer to letter A. So this was A. And now let's take a look at part B. So it says, part B, convert this range to miles per hour. Great. So basically what I have to do is I'm looking to do two conversions, right? I have to convert this value here, the upper value to miles per hour, and then convert the lower value to miles per hour. Okay, so let's do that. So let's write down 94.5 kilometers per hour. We have to convert that into miles per hour. So I like to think about it as a three-step process, but we really only have to do one step, right? Convert kilometers to miles, that would be the first. The second step would be to convert hours into the unit of time in our answer, but they're the same, right? So we don't even have to do this step 2, right? And then step 3 would have been to divide the numerator by the denominator. So we don't have to do anything past the first step. So just take 94.5 kilometers on the bottom, miles on the top, and they gave us the relationship, right? If you look back in the problem, it said 1 kilometer is equal to 0.6214 miles. So 1 kilometer, 0.6214. Kilometers cancel. Just take that and plug it into the calculator. So 94.5 times 0.6214. Great. Get a value, I'm going to round slightly, of 58.7 miles per hour. Okay, that's the upper limit. And then the second part now was going to be to take the 85.5 kilometers per hour and convert that into miles per hour. And so let's take 85.5 kilometers, same process, kilometers on the bottom, miles on the top, plug in the numbers, 6214, kilometers cancel. Simply do the math now. So 85.5 times 0.6214, 53.1 miles per hour. And there is the lower limit now. Okay, so we have our upper limit of 58.7 miles per hour, and we have the lower limit of 53.1 miles per hour, and that would be the range. Number 14. An infant's pulse rate is measured to be 130 plus or minus 5 beats per minute. What is the percent uncertainty in this measurement? Okay, so let's write down a formula for percent uncertainty. So percent uncertainty, I'm going to abbreviate it as UNC, would be the uncertainty associated with the measurement. So the uncertainty of the measurement divided by the actual measurement. Okay, times 100. So let's go back to what's given in the question or in the problem. So an infant's pulse rate is measured to be 130 plus or minus 5 beats per minute, right? So in that number, 130 plus or minus 5, which of the two values represents the uncertainty? Yep, the 5 does, right? So this is the uncertainty associated with it. How do we know that? Well, this value here has a certain structure. So it's basically the number or the measurement plus or minus the uncertainty. That's always how it's going to be framed. So I know that the uncertainty associated with this measurement is 5. Okay, so to find the percent uncertainty, let's take the uncertainty that's found in the measurement, which we said was 5. So we can take that and plug it in for the measurement, right? The uncertainty of the measurement. So that'll be 5. Then divide it by the measurement itself. So the measured rate was 130 beats per minute. Right? So that's now going to be the number that we're going to plug in for the measurement. So 130. And then don't forget to always multiply by 100 when we're talking about a percent. So just take out your calculator. 5 divided by 130. Multiply that by 100. And that should come out to a value of approximately 3.85%. Number 15, letter A. So suppose that a person has an average heart rate of 72.0 beats per minute. How many beats does he or she have in a 2.0 years? And then B would be 2.00 years and C would be 2.000 years. Okay, so first, in order to approach this problem, just remember the quick rules for significant figures. If you're a little confused as the rules, this is going to be a brief overview. We have another video that'll give you a little more detail on that. So let's just say I take the value of 3.0 and I'm going to multiply that number by 2. What do we get? You might say, okay, 2 times 0 is 0, right? 3 times 2 is 6. And since I have one decimal position here, I move the decimal on over one spot, right? So it should be 6.0. Okay, let me get rid of the arrows. So it should be 6.0. Now, mathematically, you would be correct. That's the answer. But scientifically, that's not correct. So here's how we have to think about it. The number of sig figures in the first value is 2. The number of significant figures in the second value is 1. Therefore, the number of significant figures in your answer can only be 1, not 2. So the rule is this: whichever number of significant figures is least in the numbers that you multiply together will be equal to the number of significant figures that your answer must have. So the answer needs to have only one significant figure, but at the moment we have 2. So, like I said, mathematically this is correct, but scientifically it's not. So what I need to do is take 6.0 and turn it into one sig fig. So just 6. That would be the scientific answer considering the correct number of significant figures. So this is the logic that we're going to need in order to approach this problem. Okay? So let's go back and see what we're given. So it says that we're going to have to, we want to find out how many beats does the person have in 2.0 years if they have a heart rate of 72.0 beats per minute. So essentially what we need to do is take 72.0 beats, I'm going to label that as a B, per 1 minute, and then convert that into beats per year. After we do that conversion, then what we can do is we can simply take that answer and then multiply it by the number of years. Okay, so this is essentially the outline, right? So let's take beats per minute and convert that into beats per year. So remember, I like to think about this in a couple of parts. I'd first convert the numerator values, but I notice that the units are the same, so I don't have to worry about that part. Okay, so that's going to remain the same. The denominators, though, I notice that they change, and it goes from minutes to years. Right, so I'm going to need to do that as my first step. Then after that, I will divide the numerator by the value of the denominator. Okay, that's going to be the second step of this problem. And then last but not least, multiplying it by the number of years would be the third step. Okay, so let's look at this in pieces. So step number 1, take 1 minute and convert that into years. Okay, so let's write down what we're given, 1 minute. Minutes on the bottom, I can't put years on the top. Reason being is I don't know how many minutes there are in a year. But I do know how many minutes there are in an hour. So that might help me get to years. Right, there's 60 minutes in an hour. So the minutes cancel. Now I got to get rid of the hours. So the hours go on the bottom. I still don't know how many hours there are in a year, so I guess I got to go to days, right? We do know how many hours there are in a day. 24. Now I have days. So that goes on the bottom because I have to cancel it. And I'm thinking, do I know the relationship between days and years? And we do, right? There's about 365 days in a year. All you who want to be technically correct, there's really 365.25 days, but we're keeping it simple. So now let's do the math. So it's basically 1 divided by 60 times 24 times 365. That gives me an answer of 1.9 times 10 to the minus 6 years. Okay, great. So that's the answer to the first part. Now step 2, just going to change the color. Just put this in gold. Make it a little more colorful. Little happy tree over here reminds me of Bob Ross. Anyway, don't mind me. So step number 2 now will be to take the beats value. Now remember, the beats value was 72 beats. Okay, so that's the beats value, 72.0 beats per now the number of years I just calculated. So 1.9 times 10 to the minus 6 years. And when I do this division, I now find the value of beats per year. So plug that into your calculator. Okay. So it should be a large number, right? That makes sense. So it comes out, I'm going to round slightly. It comes out to about, looks like it's going to be 30 or 3.78 times 10 to the, let's count the decimal places, 7 times 10 to the 7 beats per year. That's per 1 year, right? Okay, great. Now that's the answer to the second step. And last but not least, we have now our third step, right? Our third step now, we have to then take the beats per year and multiply them by the number of years. So here's where we have to be considering significant figures. Okay, so step 3. Now, oh, by the way, if you look back to here, I went down to 2 significant figures. I could have kept it really at 1. It's an exact 1 minute value. So I just rounded to 2. You could have had 3 or more. It doesn't matter. As long as though your final answer here will have 3. Technically, when I divided by the 2, I should have had 2 significant figures in my answer. But they're exact values in the denominator. So just disregard that little fact. I think the value was actually, it wouldn't even matter because it was really a 1.90. So I'll just add that in here to make it technically complete. So now I had 3 significant figures divided by 3 significant figures, and therefore my answer should have 3 significant figures, which it does. Okay, not to get too lost here. So now let's take the beats per year, which is 3.78 times 10 to the 7 beats per 1 year. And now let's multiply that by, for part A, multiply that by 2.0 years. Now notice the years will cancel, and that will leave me with beats. Okay, not the headphones, but the beats of a heart. So all I have to do now is multiply it together. So multiply that number by 2, and we get now about 7.5686400, right, all that. But remember, your answer cannot have more than 2 significant figures. Why? Because this number in the front had 3 significant figures, and this second number has 2. Therefore, your answer can only have 2 significant figures. So I have to do a little rounding, so it should be 7.6 times 10 to the, should be the same exponent, 7 beats. That would be the answer to part A. That's the final answer. Now for part B, right? For part B, The only difference is now, if you go back to the problem, they're just now talking about 2.0 years. So we're even a little more accurate. So let's do the calculation here. So it'd be 3.78 times 10 to the 7 beats per 1 year. I'm going to multiply that now by 2.00 years. Now notice I have 3 significant figures in the first number, 3 significant figures in the second number. Therefore, my answer now should have 3. So when we do the math, right, you don't even have to plug it in again to the calculator. You can just use the number that's there already. But the number should be 7.57 now. 7.57 times 10 to the 7th beats. Okay. And last but not least, now part C. Right, so part C says now, how many beats are there in 2.000 years? So let's do the math down here at the bottom. So let's take the number 3.78 times 10 to the 7 beats per 1 year. And now let's multiply that by 2.000 years. Notice the years cancel, leaving me with beats. So that works out. Now, make sure you go back and analyze the number of sig figs. This number has 3. This number has 4. Therefore, my answer can only have 3. So guess what? It's actually going to be the same value as letter B. 7.57 times 10 to the 7th beats. And that would be the final answer for C. Number 16. A can contains 375 milliliters of soda. How much is left after 308 milliliters is removed? All right, so this question is fairly straightforward, right? So we can come up with a very simple formula here. So the amount you start with, right? The amount you start with, subtracted by the amount removed, shall equal the amount left. Cool. So sounds like we can just plug these in, right? So it says it initially contains 375 milliliters. That's the initial amount, or the amount that you started with. Then it's telling us that we removed 308 milliliters. And finally, it says how much is left, right? How much is left after that's removed. So therefore, that's the question actually we're trying to solve. So let's just plug in the numbers. So we have 375 milliliters minus 308 milliliters will equal now, so just plug it into your calculator, 375 minus 308 comes out to be 67 milliliters. And that would be the final answer. Just remember one thing, guys. When you do additions and subtractions and whatnot, you have to make sure that the units are consistent. So if they gave you a milliliter value for the amount you started with, and then let's say a liter value for the amount you removed, you would have to do a conversion in that problem. You would either have to convert one value or all of them to liters or all of them to milliliters. It doesn't matter which one, as long as they're consistent. So just keep that in mind. Number 17. So state how many significant figures are proper in the results of the following calculations. Letter A. So 106.7 times 98.2 divided by then 46.210 times 101. And 1.01 that is, right? So let's take a look at A first. So what we need to do is we realize that all the operations here in this calculation deal with multiplication and division. So what that means is we will be taking meaning our answer will have the least number of significant figures, or it will match the number of significant figures of the number that had the least in the calculation. So how many significant figures does this number have? It has 4. How about this number? It has 3. How about this number? It should have 5. And then how about this number? It has 3. Now, if calculating significant figures is an issue, we do have a prior video that I'll either tag or put in the description below, and you guys can check that out. But in order to answer this question now, all we need to do is highlight what's the least number of significant figures. So it looks like the least number, right, would be 3. and I'll just box this answer right here. So that means for part A, right, the significant figures, or sig figs in the answer must equal 3. Easy enough. Let's take a look at letter B. Actually, I'll change the color. Let's take a look at letter B. So now for letter B, we're doing an operation, we're squaring, right? So it's 18.17 squared. So let's actually write that down here. So 18.1, not 18.17, but 18.7 squared. That's the same thing essentially as saying 18.7 times 18.7. Well, how many significant figures does the first number have? 3. How many does the second? 3. It's a multiplication problem, and therefore my answer should match the number with the least. So it should have 3. Okay, easy enough. Moving on now to letter C. So here now we're taking a number in scientific notation. And whenever you're dealing with scientific notation, it's only the coefficient that matters in terms of significant figures. This whole term basically just acts as a placeholder, so don't worry about it. So the first number here has 3 significant figures. The second number here has 4. Notice we are doing a multiplication between these two numbers, therefore choose the least. So letter C would be 3. This answer should have no more than 3 significant figures. Number 18, letter A. How many significant figures are there in the numbers 99 and 100? All right, so to lead off the answer to this question, let's just write down a couple of quick rules about significant figures. So rule number 1, all numbers 1 through 9 are always significant. So meaning if you had a value of 1, 2, 3, that would mean 3 significant figures. If you had a value of 29.46, let's say, that's a value of 4 significant figures, etc. Okay, rule number 2. All trapped zeros, I'll put a little quote there, all trapped zeros are significant. So trapped between what, right? Because trapped implies it's between something. All trapped zeros between numbers, right? So between numbers. Okay, so let me give you a couple of examples. So let's say we had the value of, 2004. Okay, the 2 is a non-zero digit, meaning it's a value of 1 through 9. 4 is also a value of between 1 and 9. Therefore, rule number 1 says that they're always significant. And now these 2 zeros are considered trapped because they're between 2 numbers. So the answer would be 4. One other example would be, let's say we had a value of 2.01900. 2 decimal points would be weird. 2, let's call it. Okay. This number would have a total of 1, 2, 3, 4, 5, 6, 7. 7 significant figures. All the values 1 through 9 are significant, and the zeros are all considered trapped. Okay, great. Number 3, third rule, all preceding zeros are never significant. Okay, so a value like, if we were to have a value like 0.000196 blah, the number of significant figures here would only be 3. Because the preceding zeros, meaning zeros that lie to the left of numbers, okay, without any numbers to the left of those zeros, all right, they're never significant. If I had put a 1 here, now all of a sudden they become significant again. But without a number to the left of those zeros, they're never significant. And then the last rule, rule number 4, depends on if a decimal is present or not. Okay, so all trailing zeros are significant only if a decimal is present. Okay, so let me give you an example. So let's say we have a number 1.0120. Okay, so these three numbers, these three values are significant, the 1, and the 2, because that's rule number 1. This 0 would be considered a trapped 0, so that's also significant. And now this is the trailing 0. Okay, so this 0 is only significant if there is a decimal present in the number, which there is. So this value will have 5 significant figures. Contrast that with something that has, I'll give this number to you, 10010. Okay, without a decimal present, this one is significant, that one is significant, and these two zeros are considered to be trapped, so they're also significant. But the last one there on the outside, that's a trailing 0, but there is no decimal present. Therefore, it's not significant. So this number would have 4. Okay, now these are the rules of sig figs. So let's go back and let's look at the numbers. So we have 99. This is really simple now, right? That's significant and that's significant. So this number should have 2 significant figures. Now, the number of 100. Here's where the book, honestly, it gets a little, in my opinion, a little sloppy here. Because they say that this number could have 1, it could have 2, or it could have 3 significant figures. Well, it depends on something then. If it could be 1, 2, or 3, it must be dependent on something, and it depends on where the uncertainty lies. But for letter A, they didn't tell us anything about the uncertainty. So what that means is that I have to fall back on using these 4 rules, right? And specifically, I have to fall back on rule number 4. So the way this number is written right now, without a decimal, there is only 1 significant figure. Okay, that's the answer. So now, 99 would have 2. 100 without a decimal has 1. If there were a decimal here, at the end of it, then it would be 3. Okay? Without any additional information, that's the answer. Now, when we turn our attention to B now, the significant figures will now actually change because we have new information. So letter B says now, if the uncertainty in each number is 1, okay, what is the percent uncertainty in each? So let's just see what this additional piece of information does in terms of the number of significant figures. So let me write both numbers, both 99 and 100, with the associated uncertainty. So if I were to do that, let's put letter B over here. Okay, so if I were to do that, it would look something like this. 99 plus or minus 1. Okay, great. And the other value would be 100 plus or minus 1. Okay, so the uncertainty will help guide us in identifying how many significant figures there are. What do I mean by that? In terms of the first value, we're uncertain to the ones place, right? So it's 99 plus or minus 1, meaning it might be 100, or meaning it might be 98. So we don't know about this value in particular, because it could change. So this is where our uncertainty lies. It lies in the ones place. Okay? So since it lies in the ones place, I'm uncertain about any value that would come after that. But I am certain about any number that comes before it. So therefore, my significant figures would be 2, just like we discussed before. Now here's where it changes for the value of 100. Again, it's plus or minus 1, so this is the uncertainty, meaning that the number that's measured could really be 101, or, well, it could range, right, from 101 to 99. Again, it's this value that I'm not sure of. So again, this goes out to the ones place, right? And therefore, just as I discussed before, if this number were to trail on longer in terms of a decimal, I would be uncertain about any number out there. But I am certain from anything to the left of that ones place, from the ones place and to the left. So that means now there are 3 significant figures in this value. So all of a sudden now, when we are given the uncertainty, I know where the uncertainty lies, therefore, and that will tell me and give me insight into now the number of significant figures. So I have to now assume that this number has 3 significant figures. And to be consistent, there should be a decimal placed in there. Okay? It has to all be consistent. Done elsewise, it's sloppy. All right. So now, and I'll also put the decimal here as well. Okay, so now we can answer the question. So it says if the uncertainty in each number is 1, what is the percent uncertainty in each? Okay, so let's write our formula down for percent uncertainty. So percent uncertainty in any particular measurement is equal to the uncertainty of that measurement divided by the measurement itself multiplied by 100. So let's first work with the value of 99. So the percent uncertainty is the value of the uncertainty, which was 1, divided by the measurement itself, which was 99, okay, multiplied by 100. So, percent uncertainty, just plug that into your calculator. So 1 divided by 99 times 100, so that works out to be 1.0101. It looks like it keeps repeating. Now remember, our answer cannot have any more significant figures than the value we used that had the least. So the value we used in our calculation that had the least was the value of 1. That only has 1 significant figure. And therefore my answer can only have 1 significant figure. So rounding this off, it would just be simply 1%. I'll put the percent sign there as well. So this would be the answer for the first part. Now for the second one, right, let's find the percent uncertainty. So percent uncertainty associated with the value of 100. So the percent uncertainty is equal to the uncertainty of the measurement itself divided by that particular measurement multiplied by 100. So the percent uncertainty is equal to the uncertainty of the measurement, which was 1, divided by the measurement itself, which was 100, multiplied by 100. So obviously we can see how the math is going to work out here. So the percent uncertainty will be equal to 1.0000%. Now again, since the value of 1 in the numerator only had 1 significant figure, my answer cannot have more than 1 significant figure. So therefore the percent uncertainty is also equal to 1%. And that would now be the answer for the second part of part B. Okay, now for part C. So let's see. So it says, which is a more meaningful way to express the accuracy of these two numbers? Significant figures or percent uncertainties? So the more accurate way would be actually basically with percent uncertainties, right? Because actually, if you go back to what we just discussed, right? If I just write down the number 100 and the writer of that value does not include the decimal, there's only 1 sig fig, and if he does or she does, then there's 3. But what happens if they forget? Well, then there's an ambiguity, right? And that's what's going on in the textbook. It says it could be 1, 2, or 3. But if we're talking about this in terms of percent uncertainties, we then will know what the uncertainty is. So now we would be writing the numbers like this. And this will now tell us where the uncertainty lies and what position we are uncertain about, meaning we're uncertain about the 1's position. So that gives us an extra piece of information, just like I was discussing before. Generally speaking, the more information you have, the better decision you can make. And therefore, it would be more meaningful to express this in terms of percent uncertainties. That would be a more accurate way to do so. Number 19, letter A. If your speedometer has an uncertainty of 2.0 kilometers per hour at a speed of 90 kilometers per hour, what is the percent uncertainty? Okay, so first thing I notice is that there is a little bit of ambiguity between the significance of the uncertainty and the significant figures found in the speed. So what am I saying? Basically, so if I were to write this value out, of the speed with its associated uncertainty, it would look like this: 90 kilometers per hour plus or minus 2.0 kilometers per hour. Okay, the issue is this. The uncertainty tells me that I do or am able to analyze the speed out to the tenths place. But the speed that is given only goes out to the ones place, assuming the decimal is present, which it needs to be actually in this problem. So the way that these numbers are presented in this question are really a little too vague, and I'm going to make it a little more rigorous. Okay? Otherwise, we're going to get values all over the place. So now, really, the speedometer should have read 90.0 kilometers per hour plus or minus 2.0 kilometers per hour. Okay? I decided to make it more precise. The other way I could have done it would be to say, well, I should actually chop that zero off and just say it's plus or minus 2 kilometers per hour. And therefore now both my uncertainty value and the measurement value would have the same uncertainty, meaning they would be known to the ones place. In this case, I just decided to go the opposite direction. But it doesn't matter. I mean, it'll matter in terms of the final answers, but I have to make one of those decisions at the beginning because otherwise the question is really improper. Okay, so that being said, let's work off of this. So now it says, what is the percent uncertainty of this measurement? Okay, so we have to remember our formula. So percent uncertainty in the measurement is equal to the uncertainty of the measurement divided by the measurement itself multiplied by 100. So now if I'm trying to find the percent uncertainty, I better know the actual uncertainty value, which we do, right? It told us it was 2.0 kilometers per hour. And then divide that by 90.0 kilometers per hour. And then multiply that by 100. Okay, now notice the units are the same, and that better be the case. Okay, if they're not the same, you have to convert. Reason being is because percents are unitless, and the units will cancel. Okay, so now all we have to do here is just plug this into the calculator. Right, so 2.0, you don't have to use the 0.0, but 2 divided by 90, multiplied by then 100, works out to a value of 2.222, right, percent. Now, the answer should have no more significant figures than the value with the least. And the numerator had 2 significant figures, whereas the denominator had 3. So my answer cannot have more than 2 significant figures. So now all I need to do is just round this slightly. So the percent uncertainty will be equal to 2.2%. Okay, great. That would be the answer to part A. So now part B, it says if it has the same percent uncertainty when it reads 60 kilometers per hour, what is the range of speed you could be going? All right, so again, same issue here. This number really should be written as 60.0 kilometers per hour. Okay, so now I'm going to use that in my calculations. So again, I need to use the same percent uncertainty formula because what we're really looking for in order to find the range, we have to find the actual uncertainty. So meaning I'm looking for this variable in the numerator. I'm looking for the actual uncertainty of the measurement divided by the measurement itself multiplied by 100. That's the formula. So it says to use this same percent uncertainty, so this will be 2.2. I want to find the actual uncertainty, and the measurement we took was 60.0, and multiply that by 100. So now when you do the math here, we're going to take 2.2, so 2.2, multiply that by 60. And remember, only 2 significant figures here. So the value will work out to be, I'm not going to include the decimal, okay, so it's going to work out to about 130. All right, that'll equal now the uncertainty multiplied by the 100. Divide out the 100, divide out the 100. So my uncertainty now is equal to, right, if we just chop that, right, we move the decimal 2 places over, it would just be simply 1.3. And again, 2 significant figures. Okay, great. So this is the uncertainty, all right, associated with the measured speed of 60.0 kilometers per hour. Now, it doesn't want to know just the uncertainty, it wants to know the range of speeds. So from here, this really is fairly straightforward. So let's just write what we know. So we know it's 60.0 kilometers per hour plus or minus 1.3 kilometers per hour. And now notice again, my uncertainty value goes out to the tenths place, and so does my measured value. If I didn't correct for that in the beginning of this problem, we wouldn't have that consistency. And that's actually a good way to check and make sure you're on the right track. The amount of decimal places found on your uncertainty better match the number of decimal places found in your measurement. Okay, so now all it wants to know are the ranges. So basically, all we need to do now is add 1.3 to 60 and then subtract, right? 1.3 from 60. So when we add it, when we add 1.3 to 60, right, we're going to get, so the upper range, I'll draw a little arrow here. And let me change the color, make it a little more colorful. So when I add the value, we get a value of 61.3, right, kilometers per hour. And when I now subtract the value, so when I subtract it, it should come out to 58.7 kilometers per hour. And now notice both of these values go out to the tenths place again. It's all consistent. So notice the number on the left is the upper range, right? And then the value on the right-hand side is the lower range. And now that would be a complete answer to the problem. Number 20, Part A. A person's blood pressure is measured to be 120 plus or minus 2 millimeters of mercury. What is its percent uncertainty? Okay, so first let's start with a percent uncertainty formula, right? So let's write that down. So percent uncertainty will equal the uncertainty associated with the measurement divided by the measurement itself, multiplied by then 100. So we're finding the percent uncertainty, therefore we better know what the uncertainty is. Now remember, the numbers or these values are always written in a certain format, meaning that if I look at this, I can create a generalized format. So they're going to give the number, or the measured number, I should say, plus or minus the uncertainty. Okay, so there's really two parts to this, the measured number and then the uncertainty value. So the 2 here in this number will represent the uncertainty value. And the 120 will actually represent the measured value. So now we have enough information we need to solve this particular question. So we have 2 over 120, or 120, multiplied by 100. Now, the percent uncertainty, before I calculate that, I got to talk a little bit about sig figs here. It appears that the 120 value only has 2 significant figures, as written. Why? Because there is no decimal present. But, and this is the weird part, but the number actually does have 3. So how do I know that? Well, they told us that they gave this to us. They said that it's 120 plus or minus 2. So what that means is that either the upper limit of the upper limit of the range is the 124, or the lower limit of the range would then be 116. But wait a minute, if this number had 2 sig figs, now my answers have 3 here. How is that possible? Well, it's not possible. So basically, this is sloppy. There needs to be a decimal here in order for this all to make sense. Okay, so it's not written in, but there should be a decimal there, and there should be a decimal here. Okay, now once I calculate this percent uncertainty, now what I do is I take 2 and divide it by the 120, multiply that by then 100, and I get an answer of about 1.6 repeating, right? So it comes out to about 1.667. But now recall, this number has the least number of sig figs, right? This number has only 1 sig fig. The number in the denominator has 2. Ooh, doesn't have 2. I added the decimal now. It has 3. So therefore my answer should only have 1. So 1.667 we would have to round to a value of 2%. Okay, so that's the percent uncertainty for letter A. Let's move on now to letter B. So it says, assuming the same percent uncertainty, what is the uncertainty in a blood pressure measurement of 80 millimeters of mercury? Okay, so let me just label this as part A. Let me change the color now. I'm going to do part B. Okay, so we'll write the formula out again. So the percent uncertainty is equal to the uncertainty associated with the measurement divided by the measurement itself multiplied by 100. So it says to assume the same percent uncertainty. So my 2% value calculated in part A will be plugged into the percent uncertainty for parts B. So I have 2%. Okay, great. Now it wants us to find, it says, what is the uncertainty? So we're looking for the numerator value. So I'll just label that as my X. And the measured value was 80, right, millimeters of mercury. So the 80 goes on the bottom. Again, I have to assume that this measured number does have two significant figures, so I'm going to place in the decimal there. So multiply this by 100. Okay, so let's go about the math now. First, I'm going to take 100 and divide it by 80. Okay, so it comes out to be 2% is equal to 1.25, right? And I'm going to 1.25x, divide out the 1.25. So now x works out to be 2 divided by that answer. It works out to be about 1.6. 1.6. Now, this will not be the final answer. Okay, this is the mathematically correct answer. However, I have to consider significant figures. And when I look back to my original calculation here, this number has has one sig fig. This number has two sig figs. And then the 100 value, it doesn't have a decimal there, but it should again. This is just a conversion between percents and decimals. So this will be an exact value, and it'll have 3. So therefore, my answer should have only 1 because that's the least number. So when I calculate the value of 1.6, I would have to round that now. And I'd round it to 2 so that we do have indeed one significant figure. So this would be the uncertainty associated with that blood pressure reading of 80 millimeters of mercury. Notice how it's the same value actually as the uncertainty in part A, and the reason why does have to deal with significant figures. Number 21. A person measures his or her heart rate by counting the number of beats in 30 seconds. If 40 plus or minus 1 beats are counted in 30 plus or minus 0.5 seconds, what is the heart rate and its uncertainty in beats per minute? Okay, so this question is a little complex, and there's a lot to it, so let's try to unpack it a little bit. Let's first work with what it's asking us to do. So it says, what is the heart rate and its uncertainty in beats per minute? So let's just recall the simple model that we can base our answer off of. Right? So really what they're looking for is for us to answer in the following way. We have to give a number that represents the measurement we're trying to find, and we're going to be then plus or minus the uncertainty associated. So they want the answer in this format. Okay. Doesn't sound too hard, but this problem is a little complicated. So now, just work with me here. So what I'm going to do now is I'm going to take this model that I just drew and kind of expand on it a little bit. All right. So instead of writing the measurement plus or minus the uncertainty, I'm going to take it one step further, and I'm going to say it's the measurement plus or minus the total uncertainty. Okay, so that shouldn't be too far of a jump. All right, and the reason why I'm stressing that the uncertainty has to be the total uncertainty is because it depends on what you're measuring and how you're calculating your measurement. For example, so just think about what's going on. We have a measured value of beats, right? So somebody measured the amount of beats. that the heart is pounding. And then somebody also measured the time. Now, there's uncertainty and what we have to do is we have to find now beats per time, aka beats per minute. So if there's associated with the first measurement, meaning the number of beats, and there's uncertainty associated with the second measurement as well, that probably means that the final value of beats per minute will have a combined uncertainty, right? Or, in other words, an uncertainty that should be higher than either of the two measurements on their own. So I think that makes intuitive sense, and what I'm going to do is I'm going to write the following formula down. So I'm going to write something like this. The total uncertainty should be equal to the uncertainty found with measurement 1 plus the uncertainty of measurement 2, plus the uncertainty if we had a measurement 3, etc. Okay, so you can apply this equation on many other types of problems. Now, instead of writing the total uncertainty as equal to the uncertainty of the first measurement plus the uncertainty of the second measurement, what we could do instead is we could always find the percent uncertainty as well, right? So we could say that the total percent uncertainty, right, should equal the percent uncertainty of measure 1 plus the percent uncertainty of measurement 2 plus the percent uncertainty of measurement 3, etc. Okay, so this is definitely going to be one thing we're going to be talking about. I'm probably going to do that in the next step. I won't do that right now. So we'll come back to that idea, but I think it makes intuitive sense. So first, why don't we work on the idea of finding the measurement value? Okay, so part 1 is essentially going to be to try to find, so we have to find beats, which I'll label as B, per minute. Now what they gave us is they gave us beats and seconds, right? So they told us that it was 40, and by the way, when I'm calculating the beats per minute, okay, I'm going to use the base numbers. All right, I'm not going to worry about the uncertainties. So what do I mean by base numbers? I mean, so if you go back to the problem, I just underlined the 40. That's considered the base measurement of beats, and then the base measurement of seconds is going to be 30.0. So when I'm finding my base measurement number, where I have to do a division, I'm going to use the base measurements of the measurements that were given. So the beats value is going to be 40. And they gave me also 30.0 seconds. That's going to be the base unit of seconds. But somehow I have to find beats per minute. Well, I know the beats and I know seconds, so I think I can find minutes, right? So basically, if I take the 30 seconds and I convert that into minutes, that should allow me to find beats per minute, right? So essentially, of the first step, I'll break it down into maybe a couple of smaller parts, right? So let's first take 30.0 seconds and convert that into minutes. That's a good first step. So let's write down what we're given. And seconds on the bottom, minutes on the top. And now, in 1 minute, there are 60 seconds. Right? The seconds cancel, giving us the value in minutes. So what does that work out to be? That should work out to be 0.500 minutes. Okay, great. Now, why did I write it in that way? Well, you always have to take into account significant figures. So the measured quantity in the calculation was 30.0. This is what was actually measured. And this value has 3 significant figures. Therefore, my answer should have 3. Now, some of you might be saying, well, whoa, wait a minute. If I'm looking at what's being calculated here, I see that the 30.0 has 3, but the 60 has 2. So shouldn't the answer have only 2? Well, the thing about this conversion right here is that it is an exact value. It's not a measured value. What do I mean by that? There are exactly 60 seconds in 1 minute. It's not a measured value. We didn't have to take out our stopwatch to measure that. It's a known fact. So therefore, and this is a general rule about significant figures, you're only going to use the significant figures of measured quantities. Okay, so since this is an exact quantity, we don't have to take it into account. So I started with 3 sig figs, I'm going to end with 3. Okay, so that takes care of that. Now, part B of this will be to actually now find, right now we can finally find the beats per minute. Okay, so all we have to simply do is take the 40 beats that were measured and divide it by now the 0.500 minutes. Now when we calculate this, the answer comes out to be 80, right? Beats per minute. Okay. Now some of you might be saying, well, wait a minute, doesn't this number have only 1 sig fig? And this one down here has 3, and therefore my answer should only have 1. Well, it does, right? I didn't put a decimal there, so it actually does have 1. Another way to think about it really, and this is part of the confusion with a lot of the problems in this book, are that let's go back to what's given. They gave us 40 plus or minus 1. Right? So what that means is that the measured value of beats was at its upper range, 41, or at its lower range, 39. So if I don't include a decimal here, how many sig figs are there? 1. But all of a sudden I include the uncertainty associated with it, and wait a minute, now I get 2? That's not possible. So really, what needs to be placed in what's given is a decimal after that 40. Okay, that would be consistently, or I should say that would be correct, and that would be a much more consistent approach. So that's probably why some of this is a little confusing. So what I'm going to do is I'm going to add that decimal throughout now. All right, so I'm going to add the decimal to the 40 in my work, and I'm going to add the decimal to the 80 now. Okay, so we know that the beats per minute is 80 beats per minute. Okay, so what did we do? We essentially found the measurement here on the left-hand side. We found the first part to the piece of the pie, right? So we know that that's 80 decimal beats per minute. Okay, now what we have to do is we have to work on the second part, right? The uncertainty associated with the measurements. Now recall, so we're going to come back to this equation that we boxed in before. So what we're going to do is we're going to be working with the total percent uncertainty. Okay, so step 2 is to really find out the total percent uncertainty. Okay, so how do we do that? Well, it tells us that in order to find the total percent uncertainty, we need to find the percent uncertainty with the first measurement and the percent uncertainty with the second measurement. So let's break this down into A, and I'll do this part in red. We'll do that B. Okay, so first, part A here. The percent uncertainty associated with measurement 1 should be equal to the uncertainty of measurement 1 divided by the measurement itself multiplied by 100. That's just the formula for percent uncertainty. So now, the uncertainty associated with measurement 1, by the way, the beats is what I'm considering measurement 1. You could have done this, the seconds or the minutes first. It really doesn't matter. But just use what's given in the problem. So the uncertainty associated with measurement 1 was 1, right? And the measurement was 40. So take that, multiply it by 100. I'll put my decimal in there. So the percent uncertainty in measurement 1 was 1. So plug it into the calculator. 1 divided by 40 comes out, and then multiply by 100 comes out to 2.5%. But what's the problem? Well, the problem here is that in my calculations, the numerator has only one significant figure. Right? So my answer should have no more than 1. And so I'm going to have to round here. Right? So appropriately, scientifically speaking, this should be 3%. Because I have to round 2.5 to 3. Great. Now we can do the same approach for part B. Right? So the percent uncertainty associated with the measurement will be equal to the uncertainty of measurement 2 divided by the measurement of 2 multiplied by 100. So now I'm just taking the time calculations as measurement 2. So the percent uncertainty associated with measurement 2 should equal the uncertainty of measurement 2. So if you go back to the problem, the uncertainty is always the plus or minus value. So that is the 0.5, so 0.5, divided by then the 30.0, multiplied by 100. So now when I plug this into the calculator, so the percent uncertainty associated with measurement 2 should be 0.5 divided by 30. And it comes out to and then multiply that by 100, it comes out to a lovely decimal of 1.666 whatever, 7. Now go back and double check your sig figs. The numerator has only one significant figure. And therefore what that means is that the answer should have no more than 1. So what we're going to have to do is we're going to have to round this. So we have to round it now to a value of 2%. Okay. So now we have enough information we need in order to find the total percent uncertainty. Okay? So now let's add these two together. All right? So the total, I'll do it over here, total percent uncertainty is going to be equal to now 3% plus the 2%. Great. And therefore now this should equal 5%. Okay. So going back now, if we look back at our model, right? If we look back at this one, I wrote down here the that the measurement will be plus or minus the total uncertainty. Okay, that's great. So I have total percent uncertainty, and maybe from here I can finally figure out now the total uncertainty. Okay, so let's take a look. I'm going to write this up at the top. Actually, I'll write it right in the middle. All right, let me put this in gold. So this is essentially now the third step of the problem. Okay, so instead of also, by the way, so here's the number, the measure, actually, let me put in the number now. So 80, we have 80 beats per minute. And what we could do is we could do plus or minus the percent uncertainty. That would not be illegal at all, right? That's a valid way of writing it. So 80 beats per minute plus or minus 5, right? Because since 80 beats per minute was calculated by taking the two measurements into account, my uncertainty here also is the total uncertainty taking both measurements into account. So we are consistent, right, within this value. Okay, but now it didn't ask us, right, for what is the heart rate and its percent uncertainty in beats per minute. It said, what is the heart rate and its uncertainty? So this is very, very simple now, okay? All we have to do, instead of writing the percent uncertainty here, we just have to now write the total uncertainty, okay? So don't forget what the equation is. I'm going to go to the upper left-hand corner. So remember that the percent uncertainty is equal to the uncertainty associated with the measurement divided by the measurement itself multiplied by 100. So what is the percent uncertainty here? It's 5%. The uncertainty value is what we're trying to find. The actual beats per minute that we're uncertain of, not the percent of the beats per minute that we're uncertain of. So then divide that by the measurement itself, which we calculated to be 80, and multiply that by 100. So doing the math out, we could do this in a couple of ways, right? We could say that you'll take 100 divided by 80, right? And that comes out to, what is that, 1.25 multiplied by your uncertainty value. Then just divide out the 1.25. Divide out the 1.25 on both sides. So we find that our uncertainty value will be equal to 4, right? Just going to double check myself. My brain is, yeah, there we go. Okay, so it equals 4. So now this is the number we need. Okay, so this is finally the number we can plug in now for the total uncertainty value, which would also represent the uncertainty. Okay, so I'll write that nice and big right here in the middle of the page. So now it should be 80 beats per minute plus or minus 4 beats per minute. Since it's not in a percent form anymore, we can put the units in. Number 22. What is the area of a circle 3.102 centimeters in diameter? Okay, so for a problem like this, let's just draw a simple picture. So let's draw a circle. Thank God for autocorrect. Okay, so we have a circle. And let's now detail the center. And let's show the diameter, right? Because that's what's given in the problem. So let's just draw a simple diameter here. Okay, so now the diameter of this whole length here, this thing, is going to be equal to 3.102 centimeters. Okay, so then we have a picture, and let's now see what the problem is asking us to do. It says to calculate the area, right, of a circle. So we need to know the formula of a circle for the area specifically. So the area formula is going to be pi r squared. Okay, so did they tell us the radius? No, they did not. But they gave us the diameter. We just have to remember the relationship between the radius and the diameter, right? The radius is the distance between the center of the circle and the edge, whereas the diameter is the measure from one edge of the circle to the other edge that passes through the center. So it should kind of make sense that, right, the radius is going to be always half of the diameter. I can show it mathematically, but let's not get too bogged down with all the math. So let's just take 3.02 and divide it by 2. Okay, so that comes out now to be a value of 1.551. And I'm going to keep that whole value, right? My starting measurement value had 4 significant figures, therefore my ending value here should have 4 significant figures, which it does. Now what I can do is I can use this radius value in my calculation. Okay, so the area will now be equal to pi times the radius, which is 1.551 squared. Okay, so let's calculate it now, right? So it depends on, I'm going to use the exact value for pi, all right? So that's not going to be the limiting factor on my significant figures here. What's going to be the limiting factor is going to be the measured radius. Okay, so just remember that there are 4 significant figures, so my answer should have only 4. All right, so let's take pi and multiply it by 1.551 squared. Okay, so this comes out to be 7.557. And that's where I'm going to round it, okay? Now just remember, I didn't even include the units here, but just what was given was centimeters, right? So therefore, if the diameter was in centimeters and I just divided it by 2, the radius was in centimeters, and the centimeters would have been squared, and therefore my units here would have been centimeters squared. And that should be the final answer. Number 23. If a marathon runner averages 9.5 miles per hour, how long does it take him or her to run 26.22 miles? Okay, so we can set up actually a simple proportion in order to in order to find the answer, right? So let me set up the proportion. So I'm going to write miles 1 over hours 1 should equal miles 2 over hours 2. Okay, so this value that was given in the problem, right, 9.5 miles per hour. Well, that was per 1 hour. All right, so that value I'm going to plug into one side of my proportion. So I'll plug it into the left-hand side. So we can write 9.5 miles per 1 hour. Okay, great. Now what we're going to do is we're going to look to plug in values onto the other side. All right, so they're asking us how long does it take him or her to run this 26.22 mile marathon. So it sounds like they're asking for a time, right? So we don't know what the time here is in hours, okay? And they want us to find the time associated with a 26.22 mile marathon. So that they gave us the miles, right? So it should be 26.22 miles on the top. And notice this is good because it's consistent, meaning the units of the numerator are the same and the units of the denominator are the same. And these are proportionally equivalent to one another. So therefore, that's why this proportion works. So now to solve the proportion, there's a bunch of ways to do this, right? I'm just going to do a cross multiplication technique. By the way, all the units I'm just going to get rid of. They're all going to work themselves out. Just cancel them, all right? So we'll take 9.5 and multiply it by x. So that should be 9.5x. And the 1 hour times then the 26.22 should be just 26.22. Now divide out the 9.5 from both sides. So we'll get our x value. Let's plug that into the calculator. So 26.22 divided by 9.5. So 2.76, okay? 2.76 looks like hours, right? Now just be careful. I just got to make sure we have the right number of significant figures. Okay, the least number here was 2 significant figures. Therefore, my answer should have only 2. So I'd have to round slightly. So it'd be 2.8 hours. And that would then be the final answer. That does make sense, right? Because if it took this person 1 hour to run 9.5 miles, then it sounds like it might be a little shy of 3 hours to run then about 26. Number 24. A marathon runner completes a 42.118 kilometer course in 2 hours, 30 minutes, and 12 seconds. There is an uncertainty of 25 meters in the distance traveled and an uncertainty of 1 second in the elapsed time. A. Calculate the percent uncertainty in the distance. Okay, so let's just stop there. Let's just work with letter A for right now, because there's a lot to this problem. So I'm going to write down letter A over here. So it wants us to calculate the percent uncertainty in the distance. Okay, so now remember, percent uncertainty is equal to the uncertainty in the measurement itself divided by the measurement multiplied by 100. All right, so the percent uncertainty will be equal to the uncertainty that was given. If we go back to the problem, the given uncertainty in the distance was 25. So that's the value that goes in the numerator, in 25 meters, okay, divided by the divided by the measurement of the distance, which was 42.118 kilometers. So 42.188, not 118 if that's what I said, kilometers, multiplied by 100. Okay, great. So it looks like we can just go about and calculate this. But don't do that. Why? Well, remember, in order to do this percent calculation, the units of the numerator must be consistent with the units of the denominator. Now, it doesn't matter whether they're both kilometers or whether they're both meters. It doesn't make a difference, but they both got to be the same. So what I'm going to do is I'm going to convert the kilometer value into meter. Okay, so I'm going to do that here on the side. A little star here. So what I'm going to do is I'm going to convert 42.188 kilometers into meters. Okay, so let's write down what we're given. 42.188 kilometers. The kilometers go on the bottom, meters on the top, and the relationship is that there are 1,000 meters in 1 kilometer. Great. So now let's just calculate that, right? So we can essentially move the decimal 3 places to the right. So this would be 42,000 now, 188 meters. Now, remember, you might be saying, well, wait, this has 5 significant figures and this has 4, so why does my answer have 5? Well, it's because this conversion value here, let me highlight it. This conversion value here is an exact number. It's not a measured quantity. There are 1,000 meters in 1 kilometer, period. We didn't measure it. It's a known fact. And therefore, it doesn't influence the significant figure calculations. You only take into account measured significant figures when you're calculating the significant figure total. Okay, so we found the meters. So now what we can do is we can plug that in, okay, into the percent uncertainty calculation. So let's go back. So this is equal to 25 meters. That's the uncertainty divided by the measurement now is 42,188 meters. Great, so we have consistency now. So the meters will cancel, which is appropriate because the percent is going to be unit less. And now we just do the division. So take 25 divided by 42,188, multiply it then by 100, and we get a value of 0.059. 59%. Okay? So I only have two significant figures in my answer because the numerator value only had 2. Okay, so that takes care of part A, because we wanted to calculate the percent uncertainty in the distance. All right, so now part B. Calculate the uncertainty in the elapsed time. Well, I think they made an error here. Why? Because calculate the uncertainty in the elapsed time. Well, they gave it to us. Look, it has an uncertainty of 1 second. Yep, done, calculated it, finished, B's over. I don't think they meant to do that. What I think they meant to say here was calculate the percent uncertainty. Okay, so let's do that. Let's calculate the percent uncertainty in the elapsed time. Okay, so again, I'm going to write the formula. Percent uncertainty is going to equal the uncertainty associated with the measurement divided by the measurement multiplied by 100. Okay, so percent uncertainty will equal the uncertainty associated with the measurement. So let's go back to the problem. And they told us that the uncertainty of the time was 1 second, right? So I boxed that. So 1 second. And that's now divided by the measured time. And okay, the measured time is this, right? 2 hours, 30 minutes, and 12 seconds. So I could write down 2 hours, 30 minutes, and 12 seconds. And then multiply that by 100. But what's the problem? Yeah, right? The problem is that here I have seconds, and in the denominator I have hours, minutes, and seconds. No bueno. So we have to have one single unit throughout. Okay, so what would be easiest is if we take the denominator value and just convert that into seconds. All right, so how do we do that? Well, we're going to be looking at this in a 3-step process. Okay, so 1, convert 2 hours into seconds. Okay, let's do that first. Well, actually, I'll just tell you the whole outline. So that's the first part. The second part would be to then calculate the 30 minutes or convert 30 minutes into seconds. And then the third part will be to add all the seconds. Okay, so that's just a little map there. Let me just erase it so I have enough space. So let's do the 2 hours. So 2 hours. I'm going to put seconds on the bottom. Oh, not seconds on the bottom. Hours on the bottom, right? 2 hours on the bottom. And could I put seconds on the top? Well, I'm not sure how many seconds there are in an hour. It's 3,600, by the way, but let's assume that's not familiar. I do know, though, how many minutes there are in an hour, right? So it's 30 minutes every 1 hour. So that cancels. Then put minutes on the bottom, seconds on the top, and we know that there are 60 seconds in 1 minute. Uh-oh, sounds like my dog may have just eaten the mailman. Oh, and now my son is going crazy too. Okay, so sorry about that. Anyway, I love when the mailman comes. I don't know about you. But now, so we're going to take 2, multiply it by 60 by 60. So now we have 7,200 seconds, right? Because the minutes canceled. Okay, so this will be now the total amount of seconds from the 2 hours. The second part now is going to be to take the 30 minutes and convert that into seconds. So let's write down 30 minutes, right? Minutes on the bottom, seconds on the top, 60 seconds in a minute, get rid of the minutes. So take 30, multiply it by 60. That should come out to 1,800 seconds. Great. Now, the third part, right, is now going to be to add these 3 together. Okay, so I'll put it as over here. The third part now is going to be to take the 7,200 seconds, add to that the 1,800 seconds, and then don't forget about the 12 seconds. All right? So we'll add all of them together. So plus 1,800. I don't even need a calculator for this, but I went to it anyway. So 9,012 seconds. Great. And actually, yeah, so that's perfect. So that's 9,012 seconds. Let me just double check my significant figures here. So 2 hours. Yeah, because we were certain that it was 2 hours. So this is good. Okay. And the 30 minutes was fine. Really, the And it also tells us that the uncertainty lies in the ones place for the seconds. So we do have the correct number of significant figures here. So now what I'm going to do is I'm going to go back to my percent uncertainty calculation. And I have now 1 second divided by 9,012 seconds multiplied by 100. And now let's find what that value is. Multiply it by 100. So this comes out to a value of 0.01 percent. Okay. Now only one significant figure in my answer because I only had one significant figure in the numerator. All right. So now that takes care of part B. That is the uncertainty, the percent uncertainty that is in the elapsed time. Okay. So now let's move on to part C. And by the way, if you guys are studying out of this book, this problem really piggybacks off of problem number 21. So this actually breaks it up a little better in terms of, the question is just broken up in terms of the steps that are necessary. Question 21 actually just throws it all together. So you can think if question number 21 was hard, this one should help you out a little bit. If this one was a little hard and you want a little more practice, go back to question number 21. Okay, so now letter C. So letter C, it says, what is the average speed in meters per second? Okay, so let's, let me see. Let's write down what we know, right? So we know the total. So actually, let me write down the measurements associated with their percent uncertainties, okay? So I'm going to do that here on the upper left. Okay, so for the distance, we have a value of 42,188 meters, right? Plus or minus 0.059%. As well, 0.059% of what? Well, percent of this. Okay, I'm just going to leave it though in terms of percent for now. The time, right, would be written like as 9,012 seconds plus or minus 0.01%. 0.01% of what? Well, 0.01% of the 9,012 seconds. Okay, so now what we need to do, it says in C, again, it says what is the average speed in meters per second? So what we need to do is we need to calculate meters per second. So go back to the upper left-hand corner and look, I know the meters and I know the seconds, the base numbers, right? And that's how we're going to calculate the meter per second value, by using the base numbers here, by using the measurements, okay? So all I have to do is simply, well, probably shouldn't write an equal sign, but all I need to do now here is plug in the meter value. So we have 42,188 meters, and then plug in the second value, which was 9,012 seconds, and now calculate the meters per second. Okay, so let's do that. So we have 42,188 divided by 9,012. So we get a value of approximately 4.681 meters per second. Now, again, I have four significant figures here because the value in my calculation with the least had 4. So therefore, they should match. Okay, so that's the answer for part C, 4.681 meters per second. Okay, now part D. It says, what is the uncertainty in the average speed? So, okay, so let's consider that, So let's consider that in order to calculate the uncertainty in the average speed, or let me start here. In order to calculate average speed, we had to take the meters and the seconds together, right? Now remember, there was an uncertainty associated with the meters, and there was also an uncertainty associated with the measurement of seconds. Now, if you think about it, if I now basically took those two uncertainties and put them together in a single value, right, of meters per second. Now that's a single value; it's a ratio. I haven't doubled the uncertainty, but I have two layers of uncertainty, right? I have uncertainty associated with the meter value. Then I have uncertainty associated with the second value. So we can come up with this general equation, right, for uncertainty here. So part D, let's think of this, that the total uncertainty, right, and I have to do this in terms of percent because it's not an absolute. So the total percent uncertainty should be equal to the percent uncertainty of the first measurement plus the percent uncertainty of the second measurement plus the percent uncertainty of the third, etc. Now we only have two measurements here, both the distance and the time, right? Both the meters and the seconds. So I'm only worried about the first two. But if you had a whole bunch that you were taking into account, it would just, continue on forward. So let's find, or we don't have to find, but because we already did it. So in order to find then the total percent uncertainty, I need to know the percent uncertainties of both of the two measurements. And that's actually what the prior steps had us do, right? Step A had us find the percent uncertainty associated with the distance, which if you go back to part A, right, it was calculated to be 0.059. Okay? And to that percent, I'm going to add 0.01% because that's the uncertainty associated, percent uncertainty associated with part B. Okay, now to find the total, we just have to add the two together. Right, so the total percent uncertainty will now be equal to, just adding them both together, right, it comes out to be 0.069. Now that isn't the final total percent uncertainty because we have to take the rules into account for addition of significant figures. So very quickly, let me do this on the right side over here. So we would be taking 0.059 and adding to that 0.01. Okay, so we would get a value, right? The decimals here, there's a 0 here, there's a 6, and that's a 9. Now basically, when you add, it's not necessarily the total number of significant figures that's important. Meaning you're not looking at this and saying 2, and this is 1, therefore my answer should only have 1. What you're doing is you're looking at it in terms of decimal positioning. So what you want to do is find, so for example, in the second number, there's no more values over here. So what you do is you can create like a little line here. Okay? That's where essentially you're going to cut the answer off at. Okay? So what this is telling us is that we're going to cut the answer off at the hundredths place. Right? So you only know the hundredths place of the second value. You know up to the thousandths place for the first value. But you can't be any more certain than your most uncertain measurement. And your most uncertain measurement here is to the hundredths place. So therefore, your answer cannot be more certain than the hundredths place. Okay, so now what I need to do is I need to now round the number to the hundredths place. Right? So I look at the thousandths place, it's a 9, and it rounds the 6 up. Okay? So, this total percent, the total percent uncertainty becomes now, I'll just approximate it because it'll become now 0.07%. Okay, now that's the total percent uncertainty. What did they ask us though? They asked us, it said, what is the uncertainty in the average speed? Okay, well we found the percent uncertainty. So how do we now find the actual uncertainty? Okay, so it's very straightforward. Just remember the formula. It's going to go up to the upper right-hand corner. So this is part D continued. So percent uncertainty is equal to the uncertainty value divided by the measurement times 100. So the percent uncertainty is 0.07. That's what we just calculated. The actual uncertainty value we're going to find, and then the measurement that we're trying to find is we're trying to find the uncertainty associated with the average speed. So what is the average speed? Well, the average speed is what we calculated in part C here. So that is the number that goes in the denominator. So 4.681, right? You can put the units in if you want, it doesn't matter. Meters per second, multiply that by 100. So now couple of ways to find this. I'm going to multiply out the denominator. So do 0.07 times 4.681. That comes out to a value of 0.3, right? So you can, it doesn't really matter. You technically should stop it here in terms of 1 sig fig. Yeah, we'll just stop it here. So it comes out to 0.32767, but it should only have one significant figure because of the values that we're using, right? We're doing a multiplication. So I'll stop it at 0.3, and that'll now equal the uncertainty multiplied by 100. Right, so just divide out the 100. So your uncertainty value, will now be equal to 0. So move the decimal place 2 places over, 003. And what are the units, right? Because this is an actual measurement now of the uncertainty. The measurements are meters per second. And that would now be the final answer for part D. Okay, so that's the answer for part D. So long problem, it's very complex because there's conversions going on, there's percent uncertainties, there's uncertainties, right? There's numbers all over the place, there's conversions all over the place. But the problem kind of breaks down the steps appropriately, meaning moving from A all the way to D. Number 25. The sides of a small rectangular box are measured to be 1.8 plus or minus 0.01 centimeters, 2.05 plus or minus 0.02 centimeters, and 3.1 plus or minus 0.1 centimeter. Calculate its volume and uncertainty in cubic centimeters. Okay, so let's just sketch a quick picture. So we got a rectangular box, right? One of the sides is measured to be 3.1 centimeters, right? Plus or minus 0.1. The other side of the box measures, and it's three-dimensional, so let me just draw this part in 3 dimensions here. Okay, another side of the box measures, let's call it 2.05, plus, this is all in centimeters, plus or minus 0.02. And then the height of the box could be represented as, I'll draw it over here on the left, could be represented as 1.80 plus or minus 0.01. Okay, so calculating the volume, we have a rectangular box, so the volume of this object will be length times width times height. So to find the volume, simply take all the base values of these measurements with their uncertainties. Okay, so 1.80, 3.1, and 2.05, and plug them into the volume expression. Right, so the length of the box is 3.1 centimeters. The width of the box is 2.05 centimeters, and then the height was 1.80 centimeters. So let's calculate the value. So 3.1 times 2.05 times 1.8. That comes out to a value of 11.439 centimeters cubed. Now we have to take into account significant figures, so we take the value that has the least. This number has 2, and therefore our answer can only have 2 sig figs. So it appears that the volume here, and I'll just write equivalent to, so the volume is approximately 11 centimeters cubed. Okay, so that's the volume. Now we did that first part essentially, calculate the volume, and now we have to calculate the uncertainty. Okay, so remember that in order to find the total uncertainty, we have to do this in percentage terms. All right, so if we want to find the total uncertainty of a bunch of measurements together, we first have to find the total percent uncertainty. And then from there, we can use that total percent uncertainty to then find the actual value of the uncertainty. Okay, so let's take a look at how we're going to do that. All right, so first thing is we have to recall the formula. I'm going to write it down here. So the total percent uncertainty is equal to the percent uncertainty of the first measurement plus the percent uncertainty of the second measurement plus the percent uncertainty of the third measurement plus, right, the fourth measurement and the fifth, however many you have. So we do have three measurements in this problem, right? We have a length, a width, and a height. So first, let's first calculate the percent uncertainty for the length. So I'm going to write a little 1 there, okay? And I'm going to write it now on the right-hand side. So for number 1, right? The percent uncertainty, so we think about the formula, the percent uncertainty for measurement 1, or the length, would be equal to the uncertainty of the measurement divided by the measurement itself multiplied by 100. So the percent uncertainty of the length is going to be equal to the uncertainty that that length had, which was 0.1, divided by the actual measurement, which was 3.1, and then that multiplied by, that multiplied by 100. Okay, percent uncertainty of the length. So let's throw that into the calculator. So 0.1 divided by 3.1 times 100. So that comes out to a value of 3.226, right? 3.226, etc. But we have to now round this to a value of only one significant figure, because that was the limiting number of sig figs in the numerator. So this comes out to about 3%. Okay, great. So that's the value for the first one. So let's now take a look at the width. Okay, so here's the width now, the 2.5. So let's calculate the percent uncertainty associated with that. So the percent uncertainty with the width is equal to the uncertainty of the width measurement divided by the measurement itself multiplied by 100. So the percent uncertainty of the width will be equal to 0.02, because that's the uncertainty of the width, divided by the actual measurement itself, which was 2.05, and that whole thing multiplied by 100. So the percent uncertainty of the width is now going to be equal to, let's plug that into the calculator, 0.02 divided by 2.05 times 100. And that comes out to a value of 0.9756. And we're going to have to round that to one significant figure. So this actually rounds to a value of 1%. Okay, so far so good. Last but not least now, right? Let's look at the height. So the height of the box. Now we're going to calculate that. So the percent uncertainty in the height should be equal to the uncertainty of the height, right, divided by the measurement, multiplied by 100. So the percent uncertainty in the height measurement should be equal to the uncertainty of the height, which was 0.01, divided by the measurement itself, which was 1.80, and then multiplied by 100. So percent uncertainty of the height now. So throw that into the calculator. 0.01. Well, don't throw it in, type it in, but you know what I mean. 1.8 and then times 100. Okay, so we get a value of 0.555 repeating, right? So we're going to have to round that to one significant figure. So this works out to be 0.6%. Okay, so now we have all 3%. Now what I'm going to do is I'm going to come back to the total percent uncertainty formula. So here we go, total percent uncertainty will be equal to the percent uncertainty of the first measurement, which was the length, so 3%, plus then the percent uncertainty of the second measurement, which was the width, so we calculated that to be 1%, plus then the percent uncertainty of the third measurement, right, which was 0.6, and we add them all together, so we have the total percent uncertainty. And we could throw that into the calculator, right? It's just that's 4.6. That works out to be 4.6%, but we're going to have to round this to 5%, right? That would be the total uncertainty. And the reason why we do that is because of this fact, right? If I add 3% and I add 1% to that, and then I add 0.6%, right? If you notice, I have to cut the numbers here. Okay, because I only know the first value out to the ones place and the second value out to the ones place. The third value I know to the tenths place. But when you add and subtract, you can only take, or I should say your answer has to match the placement of the value that has the greatest number of places, not the smallest, meaning the decimal places. So this becomes 4.6, but we don't count that, so it becomes, we have to use the 6 to round though the 4, so that's why it's 5. Okay, so now, let's see. Okay, so we found the total uncertainty, the total percent uncertainty that is. So now we basically have enough to finally get to an answer here. So if I were to write out what we have so far, so remember we calculated the volume of this thing to be 11 centimeters cubed. So 11 centimeters cubed. And this will be plus or minus 5%. Now they wanted to know the volume and the uncertainty, not the percent uncertainty. So no big deal. All we have to do now is convert this percent into an actual number. And we can do that again by using the percent uncertainty formula. Right? So percent uncertainty is equal to the uncertainty of the measurement divided by the measurement itself multiplied by 100. So percent uncertainty was 5. That's the total. Divided by the uncertainty, which is what we're looking for, divided by the actual measurement, which was 11, right, centimeters cubed, and that multiplied by 100. So now after we do the algebra here, 5 times 11, and then divide that by 100. So that comes out to be 0.55, but notice we only have one significant figure here, so we're going to have to round this to 0.6 centimeters cubed. And that is the actual uncertainty. So now I can rewrite this measurement with its associated uncertainty as 11 centimeters cubed plus or minus 0.6 centimeters cubed. And that, my friends, would be the final answer. Number 26. When non-metric units were used in the United Kingdom, a unit of mass called the pound mass was employed, where 1 pound mass is equal to 0.4539 kilograms. If there is an uncertainty of 0.0001 kilograms in the pound mass unit, what is its percent uncertainty? Okay, so sounds a little confusing, but it's not bad. Let's work with what it's asking first. So it says, what is its percent uncertainty? All right, so let's write down the formula for percent uncertainty. So percent uncertainty is equal to the uncertainty of the measurement divided by the measurement itself multiplied by 100. Okay, so we're looking to find the percent uncertainty. In order to find this, we need to know these two variables. Okay, so we need to know the uncertainty associated with the measurement and the measurement itself. So do we know those two things? Well, I mean, yeah, I think so, right? It says if there is an uncertainty of this many kilograms. So that value does tell us the uncertainty. Okay, so we have one of the two items we need. Now we just got to look for the measurement. So remember this one thing. Let me actually just plug it in for right now. So percent uncertainty, okay, is equal to 0.0001 kilograms divided by a number that we need to use times 100. Now remember that the units here must be consistent. Okay, what I mean by that is if you have kilograms in the numerator, there better be kilograms in the denominator, right? So the only other value in this problem that has kilograms in it is found in the conversion factor itself, right? It's found in this conversion factor. And this number right here is the kilogram. So what we can do is we can use this number as the measurement value, okay, and plug that in. So now let's do that. Let's plug in 0.4539 kilograms. Notice the kilograms will cancel, and that's what should happen because percents are unitless. So let's do the division now. 0.0001 divided by 0.4539. Multiply that by 100. So we get a value of approximately 0.02203, etc. Now what we have to do is we're going to have to round this to one significant figure because of the one significant figure found in the numerator. Okay, so let's just round it. So it's going to be 0.02%. Great, so that's the percent uncertainty associated with this pound mass unit. Okay, so that was part A. Now let's take a look at part B. So it says, based on that percent uncertainty, so meaning the percent uncertainty that we just calculated, what mass in pound mass has an uncertainty of 1 kilogram when converted to kilograms? Okay, so it sounds a little confusing, but let's try to pick it apart. So first I notice what they're giving me, right? So they're saying based on that percent uncertainty, and then they're asking now about a mass in pound mass, or they're saying what mass in pound mass has an uncertainty of 1 kilogram. So they're actually giving us an uncertainty value. So notice, do you know a relationship between these two, percent uncertainty and uncertainty? Yeah, you might be thinking about, well, the formula. And you would be correct, right? So let's actually write that formula down. So I know we have it on the left, but can never hurt to keep writing this down. It's a form of essentially forced memorization. So percent uncertainty is equal to the uncertainty found in the measurement divided by the measurement itself multiplied by 100. So the percent uncertainty we just calculated, right? It said to use that percent uncertainty, so it's 0.02%. That will equal now the uncertainty, right, which they gave us was 1 kilogram. And oh, they're asking what mass, right? So, so this is actually my X value, right? My measurement itself, okay, multiplied by 100. So now we do some math. I'm going to cross multiply, right? So it becomes 0.02x equals 100. Divide out the 0.02. Divide out the 0.02. So now x, which remember represented the measurement, will now equal 100 divided by 0.002. Excuse me, 0.02. So that comes out to 5,000. So 5,000. Now I'm not going to put a decimal in here, all right? Because if I do, that means that I have 4 significant figures. But if I leave the decimal out, that means I have only 1 significant figure. And since I have 1 significant figure in my calculation, I'm going to leave it at this. Now, consider what the units are. Remember, the value of 1 in the equation represented 1 kilogram. And I just mentioned before that these units have to be consistent between the numerator and the denominator. So what that means is that the value of 5,000 is the value in kilograms. Okay, now this is the value that is associated with a 1 kilogram uncertainty. 5,000 kilograms. Okay, but is that what we wanted? Well, it said what mass in pound mass? Well, this isn't in pound mass, it's in kilograms. But we can easily convert that to pound mass because they gave us the conversion, right? So that's the last part here. So we're going to take the 5,000 kilograms and convert that into pound mass, LBM. Okay, so write down what you're given, 5,000 kilograms. Right, kilograms go on the bottom, pound mass goes on the top, and write in the relationship. So 1 pound mass is equal to 0.4539 kilograms. Great, kilograms will cancel. And now just plug it into the calculator, right? So it's 5,000 divided by 0.4539. And that works out to a value of about 11,015. Well, 16 if I round there, but it's going to be much, right? I have 5 significant figures here. I can't have 5 because the number with the least had only 1. Excuse me, that one also has 1, but really this is what's controlling because this is a measured value. So I can only have 1 significant figure. So the answer would be 10,000 without a decimal. LBM. Kind of fell off the page there a little bit, but I think you can read that hopefully. So, and that would be the final answer. Number 27. The length and width of a rectangular room are measured to be 3.955 plus or minus 0.005 meters and 3.050 plus or minus 0.005 meters. Calculate the area of the room and its uncertainty in square meters. Okay, first thing, let's just draw a quick picture. So we have a rectangular room, and one side measures 3.955 plus or minus 0.005 meters, and the other side measures 3.050 plus or minus 0.005 meters. Okay, great. So it's asking us to calculate the area and its uncertainty. So let's just focus on the area first. So the area of a rectangle is length times width. Now what values do you use in this equation? Well, you're going to use the measurement values, or the base values of your measurement with its associated uncertainty. So meaning you're going to be using this number, because that's the measurement, and this number, because that is the measurement. So let's plug them into the area equation. So area is equal to 3.955, and that is in meters, multiplied by, I'll just use a parenthesis, 3.050 meters. Okay, great. So now the area is just equal to the multiplication of these two. So 3.955 times 3.050. And the answer works out to be 12.06275. And we're going to round that, right, to 4 significant figures. Why? Because each of the measured values has 4 significant figures in them. Okay, great. So this answer will be approximately 12.06. And that's meters squared, right? Since those were the units. So that's the area. Okay. Now I have to figure out its uncertainty. But remember, well, they didn't ask for percent uncertainty, so they actually want to know the actual measured uncertainty. But the only way to do this is through the percent uncertainty. Okay, so whenever you have to find the total uncertainty between a couple of measurements, well, a couple, it could be a few, right? 2, 3, 4, 5, whatever. You have to think through percent uncertainty. So the formula is this. So the total percent uncertainty is equal to the uncertainty, the percent uncertainty, that is, percent uncertainty of the first measurement plus the percent uncertainty of the second measurement plus the percent uncertainty of the third measurement, etc. So we only have 2 measurements in this problem, so that we only need 2. So let's first work with, let's call the length the first measurement. Okay, this will be number 1. Okay, so the percent, I'll give myself a little room here. So the percent uncertainty of the length, right, is equal to the uncertainty of the measurement divided by the measurement itself multiplied by 100. So the percent uncertainty of the length will be equal to the uncertainty in the measurement, and they told us it was 0.005 meters. The measurement itself was found to be 3.955 meters, and that's multiplied by 100. So this is fairly straightforward, percent uncertainty of the length. So let's do that. So we got 0.005 divided by 3.955, and then multiply that by 100. So we get a value of 0.126, and we have to round that now to 1 significant figure because of the 1 sig fig in the numerator there. So we have 0.1%. Great. Now we have to do the same thing for the second measurement that I'm going to highlight here in gold. So here now the percent uncertainty of the second measurement, or the width in this problem, would be the uncertainty associated with the width divided by the measurement itself of the width multiplied by 100. Okay, so the percent uncertainty of the width is going to equal the uncertainty associated with the width, which was 0.005 meters. divided by the measurement itself for the width, which was 3.050 meters, multiplied by 100. So the percent uncertainty associated with the width is equal to, now take out your calculator again, 0.005 divided by 3.050. Multiply that by 100, and it comes out to be 0.1639, etc. And we have to round this guy to 1 sig fig, again because there's 1 sig fig in the numerator. So it works out to be 0.2, right? 0.2%. Okay, great. So we found the percent uncertainty associated with the length and the percent uncertainty associated with the width. Now we can finally find the total percent uncertainty associated with both the length and the width. And the reason why we need both the length and the width is because we calculated the area. And the area included the length and the width. So the percent uncertainty of the length, right, was 0.1%. And the percent uncertainty associated with the width was 0.2%. So adding those together, we get the total percent uncertainty to be 0.3%. Okay. Now we can write our area with its associated percent uncertainty. So let's take a look at what that looks like down here on the left. So it would be 12.06 meters squared plus or minus 0.3%. Okay, well 0.3% of what? Well, 0.3% of the measurement. So that would be the answer if they wanted it in, they wanted you to calculate the area and its percent uncertainty. But they asked us to calculate the area and the uncertainty, not the percent. So no big deal. All we need to do is another calculation. So recall the formula, right, that we have written 14 times on the right-hand side. Well, not 14, right, but a few times. Percent uncertainty with a measurement is equal to the uncertainty of the measurement itself divided by the measurement multiplied by 100. So we calculated the percent uncertainty, the total percent uncertainty, to be 0.3%. Now what I want to do is I want to actually find the value of that uncertainty. And in order to do that, I need to know the mass. The measurement. And we do, right? The measurement was area. So we plug in the area value down here, okay, in meters squared, and that will then be multiplied by 100. And when I do this math, it will tell me the uncertainty in meters squared. So let's cross multiply. So 0.3 times 12.06. So this works out to be a value of 3.618. Right? Really, I should only be using 1 sig fig here. So I'm going to just backtrack slightly. Okay. So it should be 4. Okay. Equals then the uncertainty multiplied by 100. So just divide out the 100. Just divide out the 100. And now your uncertainty is equal to 4 divided by 100, right? And we can just move the decimal place. You don't even need to really put it into the calculator. So the uncertainty is 0.04 meters squared, because those are the units now in our formula. Great. So now what I'm going to do, instead of writing my measurement with its associated percent uncertainty, now I'm going to write my measurement with its associated uncertainty. So 0.04 meters squared. Okay. And that would be the final answer. Notice something else, and this should be the case, right? Notice how my answer, in terms of uncertainty, goes out to the hundredths place. And notice the value of the area also goes out to the hundredths place. That should be the case. And if you go back and look at any other problems, you'll notice that they're all consistent. That's a good way to check. Number 28. A car engine moves a piston with a circular cross-section of 7.5 plus or minus 0.002 centimeters in diameter, a distance of 3.25 plus or minus 0.001 centimeters to compress the gas in the cylinder. So A, by what amount is the gas decreased in volume in cubic centimeters? All right, so first thing is, let's just sketch a rough picture here. So over on the left-hand side, I'm going to do so. So we have this cylinder that's basically like a piston. So we draw this. Okay, now it tells us that the cross-section's diameter, right? So I'm going to draw the diameter here. So the cross-section's diameter is, draw a little arrow, is 7.500 plus or minus 0.002 centimeters. Okay. And it also tells us that this piston, or that the circular cross-section is going to be compressed, right? We're going to push down on it, and it's going to move this value, right? 3.25 plus or minus 0.001 centimeters. Okay, so let me draw that in here. So eventually it's going to reposition itself somewhere down here. Okay, and it moves the distance as I just mentioned, 3.250 plus or minus 0.001 centimeter. Okay, great. So now it wants to know by what amount is the gas decreased in volume. Okay, so the first thing is we have to recognize that we're dealing with a cylinder. Remember, it says it in the problem there. Okay, so what's the, if you recall the formula for volume of a cylinder, it will be V is equal to pi r squared multiplied by the height. Okay, so we need to know, in order to find the volume, we need to know the radius of the cross section and the height. All right, so just so that we're clear, this is basically the cylinder that we're talking about. So from this point down to here, okay, that's going to be our cylinder. So our height value is in gold here, right? That's going to be the height. And they didn't tell us the radius, right? They told us the diameter of the cross section, but that's not a big deal, right? We know we have to take the diameter and then divide it by 2. Does that make sense? Okay, so let's now plug in those values. All right, so the volume is equal to pi multiplied by the radius, which, remember, the diameter was 7.500, and I'm just going to divide that by 2 so that I find the radius, and that value will be squared, and then multiply it by the height, right? So that was 3.250. I just left out the units here, but they're both in centimeters, right? So that's good. I have to make sure that they're consistent, which they are. Okay. So now let's just take this and plug it into the calculator. So we're going to do pi times 7.5. Actually, use parentheses if you're going to do this all in one step. So parentheses 7.5 divided by 2. Close the parenthesis and then square that. And then multiply it by 3.25. Okay, so the value works out to be about 143.58, and that's centimeters cubed. Now we have to always consider significant figures. So it appears that this value here, right, has 4. This value here has 4. So our answer will have 4 sig figs. Now remember, I know that this number has 1 sig fig technically, but that's not a measured number, right? It's a number that I had to divide a measured value by in order to find the radius. So that won't count in terms of significant figures. Remember, we only care about significant figures for measured values. Okay, so we have to round here to 4 sig figs, so this will become 143.6 centimeters cubed. And that's the answer to part A. So now we have to find the uncertainty in this volume. Now remember, since we had to do a calculation in order to find the volume, we're going to then, if we want to find the total uncertainty in this calculation, we want to think about it in terms of percent uncertainties. Okay, so recall this formula, that total percent uncertainty is equal to the percent uncertainty of the first value used in the calculation plus the percent uncertainty of the second value used in the calculation plus the percent uncertainty of the third value used in the calculation, blah, 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 blah. Okay, so What values did we use in the calculation of the volume? Well, go back to the picture. We used the diameter value, which we converted into the radius, and we also used the height, right? So those were the values. Now, we used two values, but be careful. We really used the radius twice, right? What do I mean by that? So focus on this part here, right? Really what I did in terms of the calculation, or if we were to think about how we multiplied these numbers together, I can rewrite that equation to look like V is equal to pi multiplied by 7.5 over 2. Now, just to make this easier, let's just do that division. Okay, so that number works out to 3.75. So I really took 3.750 times 3.750 and then times 3.250. So although I used two measurements, I really calculated three measured values in the formula, right? 1, 2, and 3. So going back to the total percent uncertainty formula, remember, in order to find the total percent uncertainty, we have to find the percent uncertainty in the first measurement of the first measured value that we use in our calculations, plus the percent uncertainty of the second value that we use in our calculations, plus the third, plus the fourth, plus the fifth, etc. Okay, so basically, right, each one of these values I need to find the percent uncertainty for. Okay, so first let's talk about finding the percent uncertainty with respect to the radius. Okay, so let's write that over here. So percent, uncertainty of the radius will be equal to the uncertainty of the radius divided by the measurement of the actual radius multiplied by 100. Now remember that the diameter was 7.500 plus or minus 0.002, right? And in order to find that was the diameter. And now in order to find the radius, I had to divide this value by 2. But in order to, not only did I divide or needed to divide this magnitude value, I also have to divide the uncertainty by 2 as well. So therefore, when I write the radius, it should look something like this. Now, with its associated uncertainty, it should be 3.750 plus or minus 0.001 will equal now the radius. Okay, and that should make sense, right? If you think about right, the uncertainty when you measured the diameter should be larger than if you were to measure the radius, okay, because it's a longer measurement. So now, this is really the value that I'm considering when I'm talking about the radius. Its measured value with its associated uncertainty. So, to find the percent uncertainty of the radius, we need to find the uncertainty associated with the radius, which we calculate to be 0.001. Divide that by the measured value of the radius, which was 3.750, multiplied by 100. Okay, so now we just gotta, or have to plug this into the calculator, so the uncertainty of the radius. So take 0.001 divided by 3.75, and that works out to become 2.67, right? 2.67 times 10 to the negative 4. Oops, and don't forget to multiply by 100, so it should just be to the minus 2. So let me just backtrack. So it should be to the minus 2%. Now go back and look at your calculation. There's only one significant figure there in the numerator, so therefore my answer cannot have more than one significant figure. So the percent uncertainty associated with the radius should be equal to 3 times 10 to the negative 2%. Okay. Now remember, we used the radius twice in our calculations, right? We use it twice right there as I boxed it in. So this percent uncertainty, let me just change the color. This percent uncertainty is going to be for the first measurement value and also for the second here in our formula. Now the third one that we use in our calculations is the now height. So that's the next job. That's my next step. I have to find the percent uncertainty now, percent uncertainty associated with the height. And remember, that should be equal to the uncertainty of the height measurement divided by the measurement of the height itself multiplied by 100. So the percent uncertainty associated with the height should be equal to the uncertainty of the height, which they told us, right? If we go back to the problem, here it is. This is the measured value of the height with its associated uncertainty. So the uncertainty there is 0.001 divided by 3.250 multiplied by 100. And both units are in centimeters, so they will cancel, right? And my percent will essentially be unit less, which it should be. So let's just pull out the calculator, 0.001 divided by 3.250. So the value comes out to be approximately 3.077 or so, right, times 10 to the negative 2%. But again, only one significant figure there in the numerator. Therefore, my answer cannot have more than 1, and this works out to be 3%. Not 3%, 3 times 10 to the minus 2%. Okay. Now, this should kind of make sense, right? I'm assuming that they're using the same tool to measure both the diameter and therefore the radius and the height. Notice how the height and the radius value, I'm going to circle them. Here's my radius value. Here's my height value. Notice how they're very close to one another. So if they're very close, their percent uncertainty should also be very close, in which they are. That should make sense, right? Okay. So now we have the third value that we need. So we can plug that on in. Okay. So now, great. I can now finally find the total percent uncertainty of the measurement of the volume calculation, that is. So this is just 3 times 10 to the minus 2 plus 3 times 10 to the minus 2 plus 3 times 10 to the minus 2. So now the total percent uncertainty will work out to be 9 times 10 to the minus 2. So just plug that into the calculator, right? And you should arrive at that same value. And that's in terms of percent. So that's the total percent uncertainty. Now remember, they didn't ask for the total percent uncertainty. They said find the uncertainty. So we just have to do one more step, okay? What I'm now going to do is I'm going to take my measured volume value and its associated percent uncertainty and basically put them together. So I'll do that here at the bottom. So basically I could write this, 143.6 centimeters cubed, right? Plus or minus 9 times 10 to the minus 2%. Now that would be fine if they wanted it in percent uncertainty, but they don't. They want to find the uncertainty. So what we need to do is we need to take this percent uncertainty and just convert it into the uncertainty in the measurement. So how do we do that? Well, we've basically been doing that for the past 2 steps. Think about the formula, right? I'm going to write it up here below the problem. So we have now our percent uncertainty is equal to the uncertainty of the measurement divided by the measurement itself, right, multiplied by 100. So the percent uncertainty we just calculated, it was 9 times 10 to the minus 2. The uncertainty is what we're trying to find, so that's our variable. And the measured value was 143.6. Multiply that by 100. Now simply solve this, just do the math and solve for the uncertainty. So 9 times 10 to the minus 2 multiplied by 143.6 and then divide out the 100. Okay, so this works out to be the uncertainty here in this measurement is now going to be, hold on one second. Great, so this one works out to be 0.129, etc. Okay, now only one significant figure in your calculation here, so therefore my answer cannot have more than 1. So the uncertainty here would be equal to 0.1. Okay, so that's now the answer. That would be the answer for letter B. Okay, and let's just rewrite how this will now look with the volume and its associated uncertainty. I'm going to do that in the upper right-hand corner. So it'd be 143.6 centimeter cubed. And actually, I should have put the units in here. So let me just erase over here. Don't forget the units. This is in centimeters cubed. And then it would be plus or minus 0.1 centimeter cubed. And that would now be the measurement with its associated uncertainty. And notice a quick check is to notice where the measurement goes out. The measurement goes out to the tenths place. And my uncertainty also goes out to the tenths place. That should be consistent. If they're not, something went wrong in your calculations. So that's a good check. Number 29. How many heartbeats are there in a lifetime? Okay, so we need to make a couple assumptions in this problem, right? So two things we need to do. So we need to find an average amount of heartbeats. Probably the best way to do this would be to find the average number of heartbeats per minute, right? So let's think of an average heartbeat value per minute. Again, there's no really right answer, but once we choose the average value, we will have a then correct answer. So let's just assume that there's 60 beats, right, per minute. That's the average heart rate. We also now need to figure out, right, what the average lifetime would be. Just to make it easy, why don't we assume a 70-year lifetime? Okay, a little higher, a little lower, it doesn't matter. But that's just what we're going to assume here in this problem. So basically what I want to do is if a heart beats 60 times per minute, how many times will it beat then over 70 years? Okay, so one way to approach this, right? So let's write down 60 beats per 1 minute. If I can convert this value into essentially beats per year, then I would know, right, the number of beats in a single year. And then if I were to know the number of beats in a year, I would just have to take that and multiply it by the number of years, right? And that would then give me the, right, total beats over a lifetime or over the 70 years. So let's first work on this conversion of 60 beats per minute and convert that into beats per year. Okay, so I notice the numerator values are the same, so I don't have to do anything there. When I look at the denominator value, I do notice that there is a change in unit, right? So this is really how I'm going to start my conversion. So I'm going to look to convert 1 minute into years. Okay, so let's write down what we're given, 1 minute. I'm going to put minutes on the bottom. I can't put years yet on the top because I don't know how many minutes there are in a year, but I do know how many minutes there are in, let's say, an hour, right? 60 minutes in an hour. So the minutes would cancel. Then I'm going to write hours on the bottom. And now I'm thinking, well, I do know how many hours there are in a day, right? So I'm getting closer to a year. So there's 24 hours in a day. Okay, so the hours cancel. Then I got to write day on the bottom. And now I'm thinking day, do I know how many days there are in a year? Oh, yeah, right? We do. So let's just approximate it, right? There's 365 days in 1 year. So that will now get me the amount of years that 1 minute is equivalent to. So let's do the math, right? So it'll be 1 divided by all these values, 60 times 24 times 365. So that works out to be a value of 1.9 times 10 to the minus 6 years. Okay, great. Now what I'm going to do is this is my year value. Okay, so I'm going to take the original beat number, the 60. So now I'm going to write 60 beats per 1.9 times 10 to the minus 6 years, right? Because that is the same thing as a minute. So I can do this division now, and when I do the division, I find a value of, looks like 3.1536, right? 3.1536 times 10 raised to the 3, looks like 7, right? Raised to the 7. So beats per year. So that's a lot of beats. Now, I have to round this a little bit, right? Let's assume that it's 60 beats per minute, and I put the decimal here. Okay, so there I'll put in the decimal here again. So let's assume that now, and the 1 minute value, let's also assume that I counted it out to 1.0 minutes. Okay, just so we can have two significant figures here. I'm just tweaking it slightly, not a big deal. So my answer now should have two significant figures. So let's do 3.2 times 10 to the 7 beats per year. Okay, great. So that's the number of beats per year. So that got me to this value. Now I know if I know the beats per year, I can just multiply it by the number of years. And that'll get me now the total beats. So let's do that step. Okay, so this was essentially part 1 that I just did. Right, now let's look at part 2. I'll write it over here. So let's take our 3.2 times 10 to the 7 beats per year and multiply that by 70 years. Right, if we notice, the years are going to cancel, leaving me with the total number of beats, and that's exactly what I want. So multiply it by 70. And now take that value, I'm just going to write it underneath here. So wow, that's a huge number. So it'll be 2.2, and again, two significant figures. I'll assume that my 70 year had a decimal point there. So 2.2 times 10 raised to the, I'm going to count this one out, 3, 6, 9. Wow. Okay. Raised to the 9 beats. So that's about 2.2 billion beats in one's lifetime. Number 30. A generation is about 1/3 of a lifetime. Approximately how many generations have passed since the year 0 AD? Okay, so first thing is we got to make a few assumptions. Well, one big assumption, right? We have to figure out what the average lifetime is. And let's just assume that it's 70 years. Okay, so once we know the average lifetime, if the average lifetime is 70 years, then they're telling us a generation is about 1/3 of that, right? So to find out what a generation would be, we would take 70 years. Actually, let me write it down here in the work. So we take 70 years and divide it by 3, right? And that should tell us how long a generation is. So plug that into the calculator. 70 divided by 3 comes out to about 23.3, right? We'll round this though to 23. Since we have two sig figs, I'll put in the decimal there. And that's 23. That's 23 years per one generation. Okay. Now what it says is it wants us to answer the question of approximately how many generations have passed since the year 0 AD. So as I currently am recording this video, we are in the year 2020. So the year 2020, right? 2020 minus 0 AD is obviously 2020. So in other words, 2020 years have elapsed. So now what I need to do is I need to essentially connect these two values. So every 23 years is equivalent to one generation. And, right, so I can write that over here, 23 years is equal to 1, I'll just call it G for generation. And now if 2020 years have passed, we need to figure out how many generations that is. So let's reorganize this equivalency into a ratio. I'm actually just going to flip it. Okay, so instead of writing 23 years per one generation, I'm going to say one generation is equivalent to 23 years. And now why I'm going to do that is for the following reason. Because now I can take this and multiply it by 2020 years, and notice the years cancel. So what unit am I left with here? Well, I'm left with generation. So that's all I need to do now. Right, so 2020 divided by 23, and that works out to about 87.8 Okay, 80, let me just change the color, 87.8 generations. Now again, since there's two significant figures, let's round that to about 88 generations. So that's about how many generations there would be from the year 0 AD to today. Number 31. How many times longer than the mean life of an extremely unstable atomic nucleus is the lifetime of a human? And they give us, now it says hint, right? They give us the lifetime of the unstable atomic nucleus, and it's on the order of 10 to the negative 22 seconds. Okay, so basically in this problem, what we're trying to do is we're trying to find a ratio. Okay, we're trying to find the ratio of the lifetime, I'll call it life of a human, to the lifetime of an unstable nucleus. Okay, now remember, in any ratio, especially if you're comparing two things to one another, it's best to compare apples to apples, meaning that the units must be consistent between these two. So it doesn't matter what unit you choose, meaning as far as time is concerned. You could have years compared to years. That's fine. You could have seconds compared to seconds. That's fine. But to do years per second, you could do that, but it would probably be better. It would probably be a little clearer if we were to choose the same units in both the numerator and the denominator, so we can get a true ratio of how many times longer one is than the other. So let's assume that the average lifetime of a human is 70 years. Okay, so already, right, I know I'm giving you a value in years, and they gave us the time value of the nucleus in terms of seconds. So I already know that I'm going to have to do a conversion. That doesn't matter which way you go, just choose one and work with it. So why don't we convert 70 years into seconds? So let's do that over here. So let's convert 70, I'll call it point. All right, I'll give it a decimal value. 70 years, and let's convert that into seconds. Okay, so let's write down what we're given. So 70 years. We're going to put years on the bottom, and then days on the top. Why? Because I do know this conversion, that there's 365 days in a year. There's really 365 and a quarter, but let's just keep it simple. Then I have to put days on the bottom so that they cancel. And now my next conversion would be to hours, because I know that there's 24 hours in a day. Then hours must go on the bottom so the units cancel. And now I can make the following logical leap, right? Because I know how many minutes there are in an hour. 60 minutes in an hour. And then last but not least, I do know the relationship between now seconds and minutes. 60 seconds in a minute. And now look, what's left, if you notice all the units have canceled, would be seconds. So once I do this calculation, I will find the number of seconds there are in 70 years. So 70 times 365 times 24 times 60 times 60 would be 2.2 times 10 raised to the, let's see, 9. 2.2 times 10 to the 9 seconds. So again, 2.2 billion seconds. It's a lot of seconds. Now, what we're going to do is we're going to now take this value, okay, that we just found, and this is essentially the numerator value here in my ratio, the lifetime of a human in seconds. And they now gave me the lifetime of the atomic nucleus in seconds. So what I can do is plug that in for the denominator. I'm going to do that on the bottom of the page. So now we're going to take 2.2 times 10 to the 9 seconds divided by 10 raised to the negative 22 seconds. So now let's do that division. So 2.2 raised to the 9 divided by 10 raised to the negative 22. And this works out to be some insane number, right? 2.2 times 10 to the 31. Right now it's unitless because the seconds have canceled. So what this tells me, but I can put this over 1, right? So what this tells me is that whatever time unit I use for the nucleus down here, it would be the equivalent time unit in the numerator for the human lifetime. So essentially, the human lifetime is 2.2 times 10 to the 31 times larger, okay, than the lifespan of an atomic nucleus. I've never been so happy to be human before. Number 32. Calculate the approximate number of atoms in a bacterium. Assume that the average mass of an atom in the bacterium is 10 times the mass of a hydrogen atom. So they give us the mass of the hydrogen atom, right? It's 10 raised to the negative 27 kilograms. And then they also give us the mass of the bacterium, and it's 10 raised to the negative 5 kilograms. Okay, so let's take this in pieces. So let's first find out. I know we're looking for the number of atoms in a bacterium, right? So we're going to have this bacterium. This whole bacterium is going to have a certain mass, right? Its mass will equal question mark. And it will also have a certain number of atoms within it, right? So let's draw these little circles. They'll all represent atoms. Now each atom has a mass, right? So all the atoms have a mass as well. So the mass of an atom, right, in the bacterium is, we don't know at the moment. But we do know the mass of the whole bacterium, right? It gave it to us if we look right here. So the mass of the whole bacterium is 10 raised to the negative 5 kilograms. Okay, so I actually do know this mass. So let me just erase this unknown here. So the mass here will be equal, and I'll just put it in a different color, 10 raised to the negative 15 kilograms. Okay, so, and they also tell us that the mass, they also give us the mass of this hydrogen atom, right? And they say that the average mass of a single atom in the bacterium is 10 times the mass of the hydrogen atom. So, the mass of the hydrogen atom, as they had given to us here, is 10 raised to the negative 27 kilograms. Now, if I take that value and multiply it by 10, right, this should then, and this is kilograms per atom, by the way, if I take that value and multiply it by 10, I should get the now 10 raised to the negative 26 kilograms per atom. And I'll just add one word here, per atom of bacterium, right? This ratio on the left-hand side was per atom of hydrogen. Okay, so this makes sense. So now here is the average mass of an atom that's found within a bacterium. So now, knowing this ratio and also knowing the total mass of the bacterium itself, could we now find the number of atoms? Well, I think we can, right? What I'm going to do is I'm going to take this ratio here and I'm just going to flip it. Okay, so I put the atoms of the bacterium on top. Okay, so let me do that right down here. So for every one atom that's found in the bacterium, its weight is 10 raised to the negative 26 kilograms. Now, if I take this ratio and I multiply it then by the mass of the whole bacterium, right, which was 10 raised to the negative 15 kilograms, that will now tell me the number of atoms, because notice the kilograms will cancel. And therefore, the only unit that's left would be atoms of bacterium. So that's the unit that I'm going to write down over here, atoms of the bacterium. And now all I have to do is take 10 raised to the negative 15 and divide it by 10 raised to the negative 26. And that gives me 1 times 10 to the 11, right? Atoms of bacterium. And in other words, you don't need the 1, right? It's just 10 to the 11 atoms of bacterium. And this should make sense, right? There should be a whole bunch of atoms within that single bacterium. Number 33. Approximately how many atoms thick is a cell membrane, assuming that all the atoms there average about twice the size of a hydrogen atom? Okay, so in order to appropriately answer this question, we do have to make a couple of assumptions. So let's first assume that the average thickness of a cell membrane is 10 raised to the negative 10, or actually negative 8 meters. Okay, so that's the average thickness of the membrane. We also need to estimate or look up, basically, right, the average size of a hydrogen atom in terms of its diameter. So the average size would be something like 10 raised to the negative 10 meters. Okay, and that would be the average thickness of a hydrogen atom. So that's its thickness. Okay, so now we have enough information we need now to start the problem. So they want to know how many atoms there are in a cell membrane. And they also tell us that all the atoms there, meaning in the cell membrane, all right, average about twice the size of a hydrogen atom. So, it should make sense. If we know the size of a hydrogen atom, we could multiply that by 2, right, to find the average size or thickness of the cell membrane atom. So let's do that below. So 10 raised to the negative 10 meters, right, multiplied by 2. Should now work out to be, you can take out your calculator for this, 10, you don't really need it, but you can still use it. So 10 raised to the negative 10, right, and multiply that by 2. So it comes out to be 2 times 10 raised to the negative 10. Notice how I just basically put the coefficient of 2 in front. Now this would be the thickness in meters, right, per a single one atom of the cell membrane. Okay, so what I need to now do is I basically need to now take this piece of information and the average thickness of the cell membrane, and I should now be able to come up with an answer in terms of the number of atoms. So what I need to do here is I need to flip this ratio. Reason being is because I want to find the number of atoms. So I need this value to be in the numerator. So I'm going to rewrite it here on the left-hand side. So one atom, for every one atom found within the cell membrane, it weighs 2 times 10, it measures 2 times 10 to the negative 10 meters. Now if I take this value and then I multiply it by the average thickness, right, of the cell membrane, 10 raised to the negative 8 meters, notice how the meters will cancel, leaving me with the unit of atoms in the cell membrane. So that's going to be my unit here, atoms of the cell membrane. Now all I need to do is do this math, right? So 10 raised to the negative 8, and then divide that by 2 times 10 to the negative 10. And we get an answer of approximately 50. So the cell membrane is approximately 50 atoms thick. Number 34. Letter A. What fraction of Earth's diameter is the greatest ocean depth? Okay, so to answer this question, we need to know a couple of facts. All right, so we need to know the Earth's diameter. All right, so that'll be approximately, if you look it up, it's approximately 13,000 kilometers. Okay. Also, we need to know what the average, or not the average, but the greatest depth of our ocean, of one of our oceans would be. And that works out to be approximately 11 kilometers. Okay, so now armed with these two pieces of information, we can now calculate the fraction. All right. So remember, fraction has a numerator and a denominator. So if we're trying to find the fraction of Earth's diameter, right? Since we're trying to find the fraction of Earth's diameter, that's the value that goes on the bottom. The diameter of the Earth. Okay, and then the other value, what fraction we're trying to find, it would go now on the top. So, for example, in this problem, right, the ocean depth. So ocean depth will be the numerator value. So now all we have to do is plug this in, right? So 11 kilometers divided by 13,000 kilometers. Now the units have to be consistent here in order to create an appropriate fraction. So I was nice and just gave you the values in kilometers at the start. But if one was in miles and the other, let's say, was in kilometers, you would just have to convert miles to kilometers or kilometers to miles and then make sure that you were consistent. So anyway, let's just plug this into the calculator. So it'd be 11 divided by 13,000. So that works out to a fractional value of about 8.5 times 10 to the minus 4. 10 to the minus 4. And that would be the fractional value, right? This is really over 1. You can put that over 1. That's not a big deal. But that would be the fraction. And again, no units because they canceled. Okay, so that's the fractional value in terms of the greatest ocean. Now we have to turn our attention to part B, and it says now the greatest mountain height. So let's assume that the greatest mountain height is approximately 9 kilometers. So now similar methodology here. So fraction should equal then the mountain height over the diameter of the Earth, right? And that would be 9 kilometers over then 13,000 kilometers. Again, I'm consistent with the units, so they go bye-bye. So now 9 divided by 13,000 works out to a value of approximately 6.9 times 10 to the minus 4. And that's now that particular fraction. Number 35, letter A. Calculate the number of cells in a hummingbird, assuming the mass of an average cell is 10 times the mass of a bacterium. Okay, so let's work with letter A first. All right, so we have to calculate, so what we want to know is the number of cells in a hummingbird. Okay, and they say that we want to assume that the mass of an average cell is 10 times the mass of a bacterium. So I need to know the average mass of a bacterium. If you look back in the text, it should give that value to you. The average mass of a bacterium is about 10 raised to the negative 15 kilograms. Okay, so that's the mass of a bacterium. So now it tells us, though, that the mass of one of the cells, right, in the hummingbird is going to be 10 times this mass. So what we can do now is we can take the 10 raised to the negative 15 kilograms and multiply that, which is, by the way, the kilogram, right? That's the mass of a bacterium. And multiply that by 10, and that'll now give us, so this would be 10 raised to the negative 14. And this would be the weight in kilograms per one cell in a hummingbird. Okay, now what we need to do is we need to now find, by using this ratio, we now need to find the number of cells in a hummingbird. Well, but we now need to also know, right, in order to answer this, we also need to know the average mass of a hummingbird. So let me draw that in up here. So the average mass of a hummingbird is going to be about 0.004 kilograms. Okay, and that you can look up on Google. Okay, so now if I know the average mass of a hummingbird, and I also know the mass of a single cell, then I can find now the total number of cells. Right, so first thing I'm going to want to do is kind of flip this fraction. Reason being, I'll write it here on the left, one cell hydrogen, one cell, the H represents hummingbird. So one cell of the hummingbird weighs 10 raised to the negative 14 kilograms. Now notice, if I then multiply this by the total mass of the hummingbird itself, 0.004 kilograms, the kilograms will cancel. And this will now tell me the number of cells that are in the hummingbird. So that's the ending unit, right? Number of cells in a hummingbird. And all I now need to do is take out my calculator, 0.004, and divide it by 10 raised to the negative 14. So this works out to approximately 4 times 10 raised to the 11 cells. Okay, wonderful. So that takes care of part A. Now for part B. It says making the same assumption, how many cells are there in a human? Okay, well, making the same assumption that the average mass of a cell in a human is 10 times the mass of a bacterium. So what that means now, for part B, is I can write that 10 raised to the negative 14 kilograms is equivalent to 1 cell in a human. Okay, I also need to know the average mass of a human. So let's just assume that the average mass of a human is 75 kilograms. All right, so now what I can do is I can do the same thing I did before. I would essentially have to flip this ratio. Why? Because I need the cells. I want to calculate the number of cells, so I need them in the numerator. So 1 cell of a human weighs 10 raised to the negative 14 kilograms. Now if I take that and then multiply it by the average mass of a human, I can then find essentially the average number of cells, because notice the kilograms cancel, leaving me with cells. Okay, so that's going to be the unit here, cells in a human. And now all I need to do is the math. Right, so 75 divided by 10 raised to the negative 14. Okay, and this comes out to a tremendously large number. Works out to be about 7.5 times 10 raised to the 15. So that would be the approximate number of cells in a human. Number 36. Assuming one nerve impulse must end before another can begin, what is the maximum firing rate of a nerve in impulses per second? Okay, so in order to answer this question, we do need to make one assumption. We need to know how long one impulse lasts. All right, so this you can look up, and it's an approximate value. It ranges because it depends on a bunch of conditions. But one impulse can last, or is equal to 1 times 10 to the minus 3 seconds. Okay, so what I need to now do, so that must be given, or we have to find that value out somehow. So now what we can do is we can take this information and answer the question. So it wants to find out the maximum firing rate in impulses per second. Okay, so what we need to do is we need to create a fraction that looks like this: impulses per second. Now notice what we found out, that one impulse is equal to 1 times 10 to the minus 3 seconds. So all I need to do is reorganize this conversion factor into a fraction. So what I can do now is plug in the value of one impulse per 1 times 10 to the minus 3 seconds. And when I do this calculation, right, plug it in, 1 divided by 1 times 10 to the minus 3, it comes out to 1,000, right? So now what we get is we get 1,000 impulses per second, per 1 second, that is. So this would represent the maximum firing rate. And that's it. Hey, you made it. Excellent work. I'm really proud of you. Great job. I really do hope the video helped. And for the next video in the series, please click this button right over here. And if you wouldn't mind giving us a hand, if you really found the video helpful, why don't you subscribe, smash that like button, and tell your friends. All right, we really appreciate it so much, and we really look forward to helping you with more problems. We'll see you soon. Bye.